Hmm.
Well, hello everyone. My name is García Oskam. I'm here with Gerardo Contreras. We are the organizers of the course. Sorry for the technical problems. It's always difficult the first time. We have, to start the course, we have Rodrigo García, who is in Swansea University, and he will give the first part of the course. And let's get started. So Rodrigo, welcome. We're looking forward to your presentation.
Thank you, Professor Herco. First of all,
I don't hear you. Oh wait, that's my.
Oh, can you hear me now?
Yes, that was my problem.
Okay. Thank you, Professor Herco, for the invitation. Thank you, everyone, for coming here. So this workshop, it's called Stability and Sustainability, Developments in Perovskite Photovoltaics. It will be divided into 4 small modules. The first module, it's a recorded session that Professor Matthew Davies sent. He's gonna join us a little bit later, but right now he's traveling. So he prepared a video for this presentation. So that will be the first bit about sustainability. And then myself and Dr. Emmanuel Peon will give the rest of the modules. I'm going to start sharing the screen to share the presentation of Professor Matthew Davies. And yeah, please let me know if there's any problem. Okay, can you see it?
I don't see it yet, but
okay, but it's black, right?
Yes.
Yes. Okay, so I'm gonna start the video now.
Good morning, everybody. Welcome to this tutorial workshop where we're going to talk about perovskite photovoltaics. I'll just share my screen.
We see a desktop. We do hear Matt.
Okay. Sorry.
Now it's blue.
Yeah, I stopped sharing now.
just keeping you up to date.
Yeah, thank you. Can you see Matt there?
It's black again.
Okay.
Good morning, everybody. Welcome to this tutorial workshop.
Is it there?
Where we're going to talk about perovskite photovoltaics. I'll just share my screen.
No, we just see a black screen. We do hear his voice, but we don't have the visual.
Okay. Sorry about that.
Sí, lo tiene que compartir.
Sí.
En la.
Pero parece que
el sonido, video,
video.
No.
Mr. Rodrigo Garcia, do you have any problem?
Yeah, I'm trying to share the video, but for some reason,
got it.
Doesn't seem to.
Well, in this case, do you know how does it start the video? It's only in black, or it has to be an image there, a kind of picture? Okay, got it.
It starts in black, yeah.
Oh, it's start in black, and then it continues. I mean, the process is like you are trying to speak in there, and then some minutes later, it's going to be appear any image there? Or do you
Come
have
again?
other problems?
Let me see if I can. Let me try again.
Sure, take your time.
Can you see the video now?
Yes, we are seeing your screen.
Okay, let's see if that works.
Good morning, everybody. Welcome to this tutorial workshop where we're going to talk.
Is it better now? Can you see Professor Matthew Davies?
No, just a black screen. Okay, so just keep going, Rodrigo. Apparently, it will appear after a minute or so.
Okay.
About perovskite photovoltaics. I'll just share my screen. So hopefully you can all see that okay. So before I start, I would just like to thank Professor Oskam, Herko Oskam, for the invitation to give this workshop and tutorial. I'm sorry I'm not live at the moment, but I'm traveling in the UK. I will be back for questions. So any questions you have on this first part of the workshop, just keep them for perhaps the coffee break, where I hope I'll be back in time to answer any questions you may have and have a bit of a discussion there. So as I said, we're going to talk about perovskites. But I'm going to start by talking about sustainability and climate change and some of the drivers for why we do work into renewable energy technologies, or certainly why I do research into renewable energy technologies. And I think we probably share a common goal there of trying to improve knowledge around emerging materials and to improve the commercial viability of photovoltaics for clean energy generation. So I'm going to discuss some of the aspects that I think are important in terms of sustainability and what sustainability means and how we can incorporate it into our research. I'd like to start as well by thanking two postdoctoral researchers on my team, two technology transfer fellows, Rodrigo and Manuel. So they deliver large.
Unfortunately, we're still not seeing anything. So,
are you sharing with video?
No, this is my video. Now we have that's your desktop, I guess.
Sorry.
Wish I could help, but I'm no good with Zoom, and especially with sharing videos.
Yeah, let me see if I can.
Rodrigo, if you insert the video in some blank PowerPoint and then share the PowerPoint, do you think?
Yeah. I saw your text. I think that might work. Let me see if I can do it quickly. Okay, let's try again. Can you see my screen?
Yes.
Can you see it now?
We're black again.
Yeah, that's all right.
It looks better.
Fingers crossed. Let's see.
All right, it's working.
Welcome to this.
Yes.
Perovskite Photovoltaics. I'll just share my screen. So hopefully you can all see that okay. So before I start, I would just like to thank Professor Özkan, Hörko Özkan, for the invitation to give this workshop and tutorial. I'm sorry I'm not live at the moment, but I'm traveling in the UK. I will be back for questions. So any questions you have on this first part of the workshop, just keep them for perhaps the coffee break, where I hope I'll be back in time to answer any questions you may have and have a bit of a discussion there. So as I said, we're going to talk about perovskites. But I'm going to start by talking about sustainability and climate change and some of the drivers for why we do work into renewable energy technologies, or certainly why I do research into renewable energy technologies. And I think we probably share a common goal there of trying to improve knowledge around emerging materials and to improve the commercial viability of photovoltaics for clean energy generation. So I'm going to discuss some of the aspects that I think are important in terms of sustainability and what sustainability means, and how we can incorporate it into our research. I'd like to start as well by thanking two postdoctoral researchers on my team, two technology transfer fellows, Rodrigo and Emmanuel. So they're going to deliver large parts of the workshop as well, and they should be there now live. So Rodrigo is going to talk about perovskite development, stability, scaling up, and Emmanuel is going to go into detail on how we can analyze time-resolved photoluminescence and steady-state photoluminescence of these interesting materials. So yeah, just before I start properly, this is where we're from. I should have introduced myself, which I haven't so far. So I'm Matthew Davies. I'm an associate professor at Swansea University, and we're very lucky in Swansea that this is our doorstep. We have a beautiful coastline, and I'm going to talk a little bit about climate change. And one of the worries at the moment for this part of the world in particular is the Gulf Stream that, of course, connects Mexico and the Gulf to the UK and to Europe, warming Europe, potentially may shift and disappear, causing probably quite catastrophic climate change for the UK and Europe. But while we have it, we have beautiful coastline, and we have a university that's built very close to the beach. So this is one of the campuses. So Swansea has two university campuses. This is the original university campus, which, as you can see, is around 50 meters from the beach. We have a road intersecting the campus and the beach, and the university decided it wasn't close enough to the beach, so we built a new campus just around the corner, around the bay in Swansea, which is really on the beach. So you can see this is the campus. This is actually, so my office is somewhere along here. I'm very fortunate to have a wonderful view of the sea, and we're right on the beach. And hopefully we can maintain our campus during impending sea level rises that are rather worrying all over the world. But that's a problem for slightly later. Okay, so the Applied Photochemistry group at Swansea, this is the group that I lead, is part of the wider specific project, which I'm going to discuss in just one moment. But the Applied Photochemistry group, what we try to do is to use photochemistry as a tool to understand the causes and consequences of stability and instability in perovskite materials. And we try to use advanced characterization to really affect and understand the sustainability of this technology. So we're trying to use these tools to study processes such as recycling, remanufacture, which, as you'll come to learn if you don't know already throughout this talk, are going to be vital for the long-term sustainability of this technology. So this is some of the work that we do. We've done a lot of research into photobrightening, photodarkening phenomena in perovskites, and again, that's going to be discussed in more detail later. We've done work on stability and in particular using steady-state fluorescence to monitor a superoxide probe to look at superoxide generation in these materials and how that affects stability. Understanding time-resolved photoluminescence, as I said, Emmanuel's going to go into more detail there. Improving light harvesting and co-sensitization and things like that. We also do a great deal of work on greener, more sustainable solvents for perovskite deposition. We're not going to talk in detail about that today because I had to keep something back for my talk tomorrow. So tomorrow, I believe it's 12:30, my lecture. So if you're interested in learning more about sustainability of perovskites and in particular solvent systems for perovskites, then come along to that. So I said we're part of the wider SPECIFIC project. So SPECIFIC is quite a large research project at Swansea University, employs in excess of 200 people at the moment. And we look at developing the vision of buildings as power stations. We call it different things these days, but basically we want to functionalize the surfaces of buildings to generate, store and release energy. So we want more from our buildings than just keeping the weather out, keeping the rain out here in the UK. We want to generate electricity. We want to store that on site and we want to use that on site. The UK, so a steel company we work with, makes around 200 million square meters of steel a year for buildings like this IKEA building. If we can functionalize just 10% of that steel with a photovoltaic device in excess of 10% efficiency, then we can generate an enormous amount of electricity, equivalent to a nuclear power station. And we need to look at these types of solutions moving forward, how we can stimulate greater uptake of renewables. We're quite unique for a university project in that we do fundamental research. We go from really fundamental spectroscopy and photovoltaic understanding through to a pilot line, which we have. So we can test really the upscaling of these technologies. And again, Rodrigo is going to discuss upscaling a little bit later. But we have world-class scaling facilities. The scaling team is led by Professor Tristan Watson, who you may have heard of, but if you're interested in certainly larger scale perovskite research, as I said, Rodrigo will discuss it, but you can look up some of Tristan's papers, and they're really pushing boundaries of hastening the commercialization of perovskites. We also believe that we need to demonstrate that technology is ready for deployment. So what we've done is we've retrofitted and built new buildings that incorporate renewable energy technologies. So we've retrofitted things like thermal collectors for heat on these two buildings. Perhaps actually I should go to laser pointer. There you are, that's slightly more professional. So we've retrofitted thermal coatings for transpired solar collectors to get thermal energy to heat these buildings, which is much needed in the UK. This is a house that we built in collaboration with Cardiff University down the road from us. And this is a carbon neutral, energy efficient house built at roughly the same cost as an average first buyer house in the UK. This is the active classroom, which is a classroom that we have on our new campus. It incorporates photovoltaics into the roof. We originally used saltwater batteries. I believe they've been switched now to lithium-ion batteries to store the electricity, and we use that energy at the point of generation. Interesting thing about this building as well is it's rather modular in design. I'm told it was put together with a single tool and can be dismantled and built elsewhere if need be. Sorry, I'm just going to have to do that. There you go. After our success in building the active classroom, we then built the active office. This is using quite state-of-the-art manufacturing techniques to build a building. So this was actually built off-site and then put into place, which meant that it could be built through the winter in Wales, which is quite a rainy time and difficult conditions for building. This was built off-site in a factory and then installed. When we had visitors to the active classroom, we would often be asked if we could make a two-story building of the same ilk, and if we could incorporate flexible photovoltaics. So you can see we have a curved roof showing off the flexibility of the photovoltaics built into the roof, and it's over 2 stories. So that's some of the things that we've achieved with the specific project, and we move forward in trying to get greater uptake of renewable energy, green energy technologies. Now I'm just going to talk about where we are currently. And this is a slide that was extremely depressing to put together. So when I was in junior school, I won't say how long ago that was, but I was taught about climate change and some of the effects. And if somebody had told me perhaps even 10 years ago, 15 years ago, that we would experience a summer like this globally with all of these extreme weather events, I would have at least thought that we'd be taking significant action. And unfortunately, we're still not doing anywhere near enough to combat these global warming problems, these climate change problems that I'm going to discuss shortly. I'm then going to move on to at least some approaches that I think we can make as renewable energy photovoltaic scientists that may help. There's certainly much wider issues, but we can talk briefly about some of the things that I think we need to do certainly a lot better. So just in 1 month or across 2 months around the world, this is just a snapshot of some of the things we've seen. Russia is on fire, California is on fire, Greece is on fire, Turkey's on fire, Italy's on fire. Canada recorded the highest temperatures on record through what is known, or what was termed, a heat dome, seeing the loss of towns and villages there. In Europe, we've also experienced floods, so significant damage across Germany and Belgium, flooding in London. In China, I believe they saw a year's worth of rainfall in 3 days, causing unprecedented floods. And you think all of this happened within 2 months. These problems are going to get significantly worse as we continue, and we need a significant change in approach if we're going to get anywhere near to combating these problems. Okay, so why are these things happening? So some years ago, in what's known as the Stockholm Resilience Center, which you can look up, they devised these boundaries, the 9 planetary boundaries, which we must operate within to be safe. And you can see this dashed line here in the center is the safe boundary. This was put together in 2015, so 6 years ago now. So obviously some things have changed slightly. So climate change is a little bit further along in this zone of uncertainty. But you can see we've certainly gone beyond the safe zone in 5 of these categories. We're beyond the zone of uncertainty in 3 of them. So this is mass extinction, for example, and the impacts that will have on our planet is unknown. So some of them we don't have enough information on yet to even quantify. So this is the worry. The other greater thing that we need to consider in all of this is all of these things are, of course, interlinked. So things that we do, things that happen, I should say, in response to human action, such as climate change, drives greater mass extinction, for example. It drives ocean acidification. So all of these things are significant problems that we face, and we need to become inherently much more sustainable. I'm sorry, this is all rather rather grim at the moment. It's not a particularly rosy outlook, but this is where we're at. Hopefully we will now see significant action taking place. So as a group, the current scientific consensus, of course, is that we must limit global temperature rises to 2 degrees. The target of 1.5 degrees, which basically was thought to ensure a risk of severe consequences would be minimized, looks all but impossible. And we'll show some data on that in a moment. It looks like we're going to hit 1.5 degree global temperature rise. And of course, that's an average. So for some areas of the planet, that's going to be much more significant than others. And we need to take that on board. But we can still avoid 2 degrees. And every point here between 1.5 and 2 degrees is vital in mitigating some of these severe consequences. And I'm going to discuss that in just a moment. I'll also discuss how actually our current actions drive us well past 2 degrees. And that's something that we need to change rapidly. And hopefully the recent IPCC report and the upcoming COP26 conference, which is going to be held in the UK, will finally deliver significant action from our leaders. So we are currently in the Holocene period of climate. If you think of the history of the planet, for years animals would have had to migrate because of the weather, and then we hit because of extreme weather, of course, and many still do. But then we hit the Holocene, which is a relatively stable period of climate, which allowed humans to develop and expand, become much more technologically aware, and all of the things that came with it. And it looks like, or at least some scientists are calling for, now moving into a new period of climate, which is less stable due to our anthropogenic activity, due to human activity. Okay, so the IPCC and IEA are major players in monitoring the state of climate change. So if you wish to read more, the recent IPCC report, which I'm going to talk about now, is on the website. So you can go and look at that. And there's also other good sources of open climate data that people may wish to follow. You can also look at I think it's the Bloomberg clock, which shows the current level of carbon emissions in the atmosphere, and you can watch that tick up as the seconds roll by. So the IPCC report, so this came out last Monday, and while perhaps not surprising to people that follow these things, is still very stark in its warnings. So I'm going to capture some of those, and then I'm going to say about why we should continue the fight to avoid further global warming. So the IPCC report now states that it's unequivocal that human influence has warmed the atmosphere. Ocean and land, and widespread rapid changes in the atmosphere, ocean, cryosphere, and biosphere have occurred. That's already happened. Climate change is already affecting every region of the globe. And you can see that data here. So this is the temperature rise to date. This is what we've observed. This is the simulated observation of temperature rise, and I think we're probably going beyond that already. And this is the natural temperature rise that one would expect without human influence. So one of the problems that we face now is that, of course, the further we go down this road of increasing carbon emissions, the greater our problems become, and the greater the challenge becomes of mitigating climate change. The IPCC report basically looks at 5 different scenarios. One scenario where we increase our carbon usage, and you think, well, of course, we shouldn't increase our carbon usage from here, but carbon-related emissions is still increasing. Then it looks at a couple of scenarios where we limit our carbon emissions to where they are around now, and then 2 scenarios where we rapidly reduce our carbon emissions to net zero and remove some carbon from the atmosphere through carbon capture technologies. So one problem we face, this is where we are. So this is the, let's take the middle one and say this is the as-is scenario, and we may continue along this path. At this level of carbon emissions into the atmosphere, the carbon sinks of the land and ocean suffer. They can't take up as much carbon relative to the atmosphere. So it's imperative that we keep it down here where we can at least sink some of the carbon into the land and the ocean. I mean, that occurs naturally, of course, that's nothing that we're doing. But basically, the further we go down this path, the greater the problems become. So these carbon sinks are going to be less effective the more carbon we put into the atmosphere. Then we look at the potential global temperature rise going forward. And again, these are the same scenarios. So best case scenario will be with achieving net zero carbon emissions and removing carbon from the atmosphere. And you can see we may be able to just about limit to 1.5 degrees, and then hopefully start to see a decline in global temperature, a slight decline in global temperature, I should say. Again, with increasing emissions, which is the path we're on, and we need to rapidly move away from, global temperature could reach in excess of 4-5 degrees by the end of the century. And in fact, in two of the different scenarios, it gets very, well, it gets close to 4 degrees here as well. So you think in the middle scenario where we keep on status quo, sorry, that's not status quo. That's at the same level of emissions now because we're increasing. So if we stop increasing emissions but carry on at a similar level, we'll be able to limit global temperature rise to just under 3 degrees. Global sea level rises are already locked in. These are much longer term effects. These temperature rises are going to cause sea ice loss, loss of some of the ice sheets. So sea level rises are now inevitable. There's nothing we can do about these. But of course, the level to which they rise is still up to be determined. So again, in our lowest case scenarios, we're going to see significantly less sea level rises than in our highest scenarios. They also looked at a very high impact storyline, which obviously shows incredibly high sea level change, and this is likely due to loss of Arctic ice sheets. But what I want to say, all that's very grim. We're very likely to hit 1.5 degree temperature rise. But what I wanted to discuss is the difference between 1.5 and 2. So immediate, swift, sustainable action on a global level to limit this temperature rise is still very, very much in our interests, of course. So if you remember, I just said we were on track to go to surpass 2 degree temperature rise by the end of the century, maybe 3 or 4 degree temperature rise. Well, just look at the difference between 1.5 and 2 degrees. And you can certainly see from this that we cannot get near 2 degrees. We can't surpass 2 degrees global warming. So I'll just read a few of these out. Limiting global warming to 1.5 degrees would reduce the number of people frequently exposed to extreme heat waves by about 420 million, with about 65 million fewer people exposed to exceptional heat waves, which would occur more frequently at 2 degrees. 61 million more people in urban areas would be exposed to severe drought in 2 degree scenario versus 1.5 degree scenario. Somewhere in the region of 200 million fewer people are projected to be exposed to increases in water scarcity by 2050 at about 1.5 degrees, if we can limit it to 1.5 versus 2. At 1.5 degrees, we lose 6%, 6% of insects, 8% of plants, and 4% of vertebrates. What that means actually is that the geographic area in which they can live is reduced by more than half. At 2 degrees, those numbers jump to 18% insect loss, 16% plant loss, and 8% vertebrate loss. So significant impacts on the biodiversity of the planet. Limiting global warming to 1.5 instead of 2 is expected to prevent between 1.5 and 2.5 million square kilometers of frozen permafrost soils from thawing. The permafrost soils in places like Siberia store massive amounts of carbon and other carbon materials such as methane. If they thaw, they're obviously going to release large amounts of carbon into the atmosphere, accelerating this process. So again, 2.5 million square kilometers of permafrost is an enormous carbon sink, which we need to ensure doesn't thaw. At 1.5 degree warming, it is expected that the Arctic Ocean to be sea ice free one summer every century. That comes down to 1 ice free summer every decade at 2 degrees. At 1.5 degree ocean warming, we lose coral reefs by about 70 to 90%. We lose them all at 2 degrees. So very stark there. You can see just the difference in a 0.5 degree. NASA produced a very nice report for those that want to read it, called A Degree of Concern, Why These Numbers Matter. And don't forget here, again, we're just talking about that 0.5 degree difference between 1.5 and 2 degrees C. If we continue as is, we're going to exceed both of these scenarios, which, as you can see from this, will be severe. Okay, so now we can move perhaps onto some more of the lighter stuff and talk about sustainability. So, of course, many of you will be interested in renewable energy technologies, maybe specifically perovskites, but photovoltaics in general. What we need to be clear about is we need significant deployment of renewable energy technologies, but also the renewable energy technologies are not sustainable or not necessarily sustainable. Just because they're renewable, it's different from being sustainable. And we have an opportunity now to ensure that the next generation of technologies, such as perovskites, are sustainable, renewable technologies. And I'm going to talk about our usage of materials and things like that, which will help hopefully paint that picture. So if you think about the definition of sustainability, the word sustain, in fact, is Latin, to withstand. So it's about meeting the needs of the present without compromising the ability of future generations to meet their own needs. It has 3 pillars: environment, society, and economy, and all are equally important for sustainability. So we need an inclusive, sustainable, and resilient future for people and planet. So we need the world to become more socially just. We need more equity, more distribution of wealth and development along those lines to achieve sustainability. We need to bring economic opportunity in what we do as another pillar of sustainability. And of course, in doing so, we need to minimize harm to the environment and hopefully pay that back in use. And if we can achieve all these three things, these three pillars, then we can make something truly sustainable. The requirements of sustainable development then, one of them is, as I mentioned, eradicating poverty in all its forms. That's really vital to achieve sustainable development. When I talk about some of the differences between 1.5 and 2 degree scenario, what isn't apparent there is a lot of those impacts will impact the poor in society more than the rich in society, as most things. So we need a fairer society to tackle climate change and global problems in which we face. There has to be sustainable, inclusive economic growth, more jobs, greater opportunities for people, reduce inequality, raising living standards, and social development, and sustainable management of natural, I'll get there in the end, natural resources and ecosystems. And to this end, the UN introduced what you might know, might be aware of as the Sustainable Development Goals. And these are the Sustainable Development Goals. I'm not going to talk about these in great depth, but all of these are interlinked. So if you're interested in number 7, as I imagine many of you are, affordable and clean energy, then we need to think wider and the opportunities this brings in terms of zero hunger. So we can provide energy for food storage, chilled food storage to get longer shelf life, for example. We can not eradicate, but certainly help towards no poverty through generation and development of jobs in installing and maintaining renewable energy systems. This brings with it economic growth. If we do it in a morally and socially just fashion, then we can get decent working conditions, reduce inequality. We can look for opportunities to reduce gender inequality. We can ingrain into our technologies responsible consumption and production. And I'm going to talk about that. And of course, the impact on all of them. So they're the ones that I wanted to pull out. But I'm going to talk a little bit more about responsible consumption and production. So a lot of our problems that we face come down to our use of materials and the way the world works, if you like, and this linear economy. So what we've done for centuries is use fossil fuels to take things. We've taken materials out of the earth, fossil fuels out of the earth. We've taken resources and we waste energy and materials in taking these resources to make things. And in making things, we create large amounts of waste. And again, we need more energy input to make those things. We give them to consumers, all of us who buy things and use things. We use them for a while and then we throw them away. And we have an energy cost of throwing them away as well. That may not directly impact us as consumers, but that's our economy. We take things, we make things, we use things, we throw them away. It's inherently incredibly unsustainable. And if you think about this, so we take, make, use, dispose. That's generally what we do. We only generate value at the point of sale. There may be some value in some recycling and things like that further down the line, but certainly not enough. So generally, we only generate value at the point of sale. So we have to think of a new system of working. And what happens is, as countries develop and their economies develop, they use more stuff. So certainly for sustainable development globally, as we improve the economic development, or the economic development improves in countries around the world, they use more stuff. This is something that we have to reduce. With it, generates enormous amounts of waste. And again, we don't have to go through all of these graphs, but clearly there is a link between waste generation and GDP. So we make more stuff, we waste more stuff, we generate more waste, and that's increasing. increasing amounts of waste and rubbish linked to our GDP. And another slide that shows, again, that linear correlation between, this time, what we call in the UK, which is waste electronics. Okay, so there is another way, and I'm going to talk about a circular economy. If you'll just excuse me for 1 second, I'm just going to stop sharing there. Sorry about that. My Microsoft Teams just started pinging, so I thought it was just going to ping in the background. So to save that annoyance, I'll just get back to this. So I'm just going to reshare my slides. So here we are, circular economy. Okay. So instead of our take, make, use, dispose economy, which sort of runs through the middle here, eventually, I'll just go back, sorry, runs through the middle here, eventually ended up perhaps energy recovery or landfill. We need to recycle materials. We need to design things better. We need to use materials more responsibly. And I'm going to talk about some of the impacts of that on PV later. But we need to design things where a user perhaps can easily maintain them. So things like a phone that you might just be able to upgrade the battery or the camera and things like that. And if it can't be maintained, perhaps it could be reused in another application. One potential application for the vast amounts of sort of batteries from electric vehicles that are going to hit the market is domestic storage of energy. So that would be a good example of reuse, redistribute without doing anything. Then you can refurbish, remanufacture. So taking things back that have failed or don't work as they should, remanufacture them into new products and resell them. We've seen recently, certainly in the UK, this becoming ever popular. People try to buy your phones back and sell remanufactured phones. And this is something that we should all get behind. We should all look for businesses that are selling remanufactured, refurbished products. Generally, as a consumer, you gain from a much better deal, if you like, and there's inherent savings to the environment. And really, the difference, I guess, in a circular economy is recycling is really one of the last things that you want to do with a material. We all see recycling as a fairly good process to do. But here what we want to do is only recycle materials when it's really vitally important. We also have to look at biological cycles and incorporation of biological materials and things like that, and how we can get parts from biological materials that are inherently more sustainable. So I'm just going to play a video now, which explains a little bit about the circular economy. So you can have a break from my voice for 5 minutes. So hopefully this will work.
Living systems have been around for a few billion years and will be around for many more. In the living world, there's no landfill. Instead, materials flow. One species' waste is another's food, energy is provided by the sun, things grow, then die, and nutrients return to the soil safely. And it works. Yet as humans, we've adopted a linear approach. We take, we make, and we dispose. A new phone comes out, so we ditch the old one. Our washing machine packs up, so we buy another. Each time we do this, we're eating into a finite supply of resources and often producing toxic waste. It simply can't work long term. So what can? If we accept that the living world's cyclical model works, can we change our way of thinking so that we too operate a circular economy? Let's start with the biological cycle. How can our waste build capital rather than reduce it? By rethinking and redesigning products and components, and the packaging they come in, we can create safe, and compostable materials that help grow more stuff. As they say in the movies, no resources have been lost in the making of this material. So what about the washing machines, mobile phones, fridges? We know they don't biodegrade. Here, we're talking about another sort of rethink, a way to cycle valuable metals, polymers, and alloys so they maintain their quality and continue to be useful beyond the shelf life of individual products. What if the goods of today became the resources of tomorrow? It makes commercial sense. Instead of the throw away and replace culture we've become used to, we'd adopt a return and renew one, where products and components are designed to be disassembled and regenerated. One solution may be to rethink the way we view ownership. What if we never actually owned our technologies? We simply licensed them from the manufacturers. Now, let's put these two cycles together. Imagine if we could design products to come back to their makers, their technical materials being reused and their biological parts increasing agricultural value. And imagine that these products are made and transported using renewable energy. Here we have a model that builds prosperity long term. And the good news is, there are already companies out there who are beginning to adopt this way of working. But the circular economy isn't about one manufacturer changing one product. It's about all the interconnecting companies that form our infrastructure and economy coming together. It's about energy. It's about rethinking the operating system itself. We have a fantastic opportunity to open new perspectives and new horizons. Instead of remaining trapped in the frustrations of the present, with creativity and innovation, we really can rethink and redesign our future.
Okay, and lots of other good resources on the Ellen MacArthur Foundation, if you're interested. I think the key word there, sorry, I'll just flick that. At the end was that innovation. This is an opportunity, particularly for the people in our field, in this room. This is an opportunity to innovate our way out of this problem, to design things that are inherently more sustainable and can operate within a circular economy. And again, if you think of photovoltaics, do we need to own solar panels as consumers? Do we need to own them, or do we just want the electricity they produce? Then the manufacturers of solar panels are encouraged to make them last as long as they can because they own them. They want them to last as long as they can, to be as efficient as possible, and they'll replace them when a more efficient material becomes available and recycle, reuse those components. So that you as consumer always get the best of the deal, and the onus then is on the manufacturer. So yes, this is an industrial economy inspired by natural systems. It's restorative by nature, regenerative by design. It decouples economic growth from consumption of natural resources. And I'm going to talk about that a little bit more in just a moment. We have to design products for durability, upgrade, repair, refurbishment, remanufacturing, and efficient recycling. So we have to think basically about the end of life of our materials. Where we can use biologically derived materials. We need appropriate business models, as discussed. We need to generate value from products past the initial point of sale. And that's the idea of leasing materials, perhaps. The concept of waste is replaced by one of resource. We need to see waste as a resource. This is enabled by a pathway to enhance global resource efficiency. Widespread use of renewable energy is vital to decouple all of our reliance on fossil fuels and fossil fuel materials. Okay, so I think I've said most of this now. But for example, in Wales, where I am, Circular economy is projected to be worth 2 billion a year to our economy, provide 30,000 jobs. Globally can yield up to 4.5 trillion in economic benefits by 2030. So there is economic possibility here, which of course is one of the pillars of sustainability. We need to include social and environment as well, but certainly we can become more sustainable as people by adopting a circular economy. And I'll just show an example of some carbon footprint savings from primary and secondary materials. So secondary materials would be those recycled, and primary materials are those mined out of the ground. So you can see here savings of carbon dioxide per 100,000 tons of material are significant. For some of these technology metals that we're interested in, we can save really vast amounts of materials. So, but we need to design things in a way that we can get these materials back easily to make this more efficient and in turn produce more energy and carbon savings. And we need the right metrics to advise all of these procedures. And still, we need to think of the waste hierarchy. We still need to reduce our materials consumption. So first one is waste prevention. The best way to prevent waste is to think whether we really need things in the first place. If we need things, then we need to design them for end of life so we can reuse them, recycle them efficiently. So nothing gets down to disposal, and we just inherently cycle materials through technical cycles. So I'm going to talk about photovoltaics now, but just to summarize 7 key elements of a circular economy. So to disrupt, we have to design for the future, adopt systems view during designs, find the right materials, right lifetimes. A lot of this will resonate with our studies into photovoltaics. So we try to find materials that are inherently more stable, that we can get devices that last longer, maximize efficiency and things like that. We need digital technology to track and optimize resource. That's going to be vital in the deployment, again, of renewables. We need to monitor PV where they drop in performance. They need to be maintained or fixed very quickly to minimize economic loss. We need to be able to maintain, upgrade, and to sustain materials and maximize their lifetime and second lives and things like that through take back. We need to rethink our business models as discussed. Waste as a resource is vital. We really need to utilize waste, particularly waste electronics. And solar technology offers us an enormous driver for technology metals. So what we can do is recycle electronic waste that's hitting the market and have photovoltaics as a product chain where these technology metals can feed in and have great impact. So we need regenerative resources. So we need to greater uptake of renewables, non-toxic materials wherever we can. Apologies. Energy resources used in an efficient way. And we need to work together. And that's work together as a scientific community and, of course, on a larger scale. We need companies, governments, etc., to work together. Okay, so now I'm going to move on to talk about sustainable photovoltaics. I have no idea how long I've taken so far, so I'll apologize to Rodrigo if I'm eating into some of his time, but I tend to do this. Okay, so our current scenario, well, I covered that in more detail about where we are in terms of global warming, but I said earlier the carbon emissions continue to rise, and they're rising by about 1.3% annually. So we know we have this enormous problem, and we're not doing much about it. We continue to burn through fossil fuels. If this continues, we're going to exceed 2 degrees and probably really closer to 4 or 5 degree temperature rise by the end of the century. So that's the bad news. And the good news is cost of renewable energy have declined enormously. Photovoltaics are competitive In large parts of the world, they're becoming cheaper and cheaper. Wind as well is being deployed in very vast amounts to develop renewable energy technology, to deliver renewable energy. Sorry, it's still lagging behind what is needed. So we still need to improve. We still need to deploy more photovoltaics, more wind. The problem is wind and solar are probably two of the technologies. You can check this on the REN 21 report, but wind and solar are on track to meet their deployment. Other energy technologies and energy saving measures are not. So wind and solar are going to have to pick up a lot of the slack for the other technologies if we're really going to meet some of these targets. So we need to deploy renewables much quicker than we are. The energy transformation must happen much quicker. So this is where we are currently. It's likely to be another 100 on top of this at least now, but 2019, 627 gigawatts in the world of solar photovoltaic capacity. Lots of jobs in renewable energy. And again, this goes hand in hand with creating that economic pillar of sustainability and hopefully social. So it creates jobs, it creates better lives for people through better opportunity. Okay, so one thing is how much PV do we need? So you think one thing we should be able to answer is, okay, so if we're gonna mitigate 2 degrees or 1.5 degrees or get close to it, how much PV do we need? Well, you won't be surprised to hear that most of the reports differ in their projections for PV deployment. One of the reports by Teskey is very interesting. So this orange line at the top is how much PV we would need to deploy by 2050 to avoid, to help avoid a 1.5 degree temperature rise scenario, which is unlikely. So I mean, this is enormous deployment, and we have to sort of try to match as high up this graph as we can. The 2 degree scenario just shows perhaps slower uptake in the beginning, but it rises quite quickly then afterwards. What is interesting to note, the number I said on the previous graph about current deployment, we're probably surpassed these two reports, the IEA and the IEA PVPS reports on the lower end. So we need PV deployment to be in the upper part of this graph, and that is looking promising. But again, we need to deploy much quicker. Emerging technologies then can also have a massive impact. So this is what's called the mass value carbon nexus, and this shows how we've developed. And I use this slide basically to show how I believe we cannot tackle climate change without adopting a circular economy. So what we have here is this black line on the top, which is mass. This is material that we dig out of the ground to make stuff. And you can see as we've, so this is a timeline on the bottom, as we've extracted more and more resource from the ground, we've created value. We've created our economies, we've made stuff, and we've created value. But hand in hand with that, we've created carbon. And that's where we need to decouple our value from our primary extraction of materials. So we need to try to limit and reduce the amount of materials we dig from the earth. We need to continue to create value, and we need to rapidly reduce our carbon emissions. So this is projected net zero by 2050, and you can see the challenge that we face in achieving that. Some of the targets or some of the figures of where we are. So I believe this is for 2019, but pretty much 85 gigatons of materials extracted from the earth, with only 9% of that cycled back. It's incredibly dissipative, unsustainable manufacturing. And then you consider that climate change and material use are closely linked. So 62% currently of global greenhouse gas emissions are released during the extraction, processing, and manufacturing of goods. So if we continue to make and use materials the way we do, we simply will not be able to limit our carbon and our greenhouse gas emissions, and we won't be able to tackle climate change. And also global material use is accelerating. We use more things. So we need to try to reduce this along the way. And then you think of some of the materials that we need to develop a cleaner energy future. So of course, this is the periodic table. And what we've done is we've colored in some of the critical raw materials here, some of the materials that we're running out of on Earth. And then we've got a color for roughly the recycling rates, the current recycling rates at end of life. So we need these materials to deliver these technologies on the right, that deliver batteries, fuel cells, magnets, phosphors, semiconductors, PV materials, battery materials, all of the things that are going to help us achieve a cleaner energy future, rely on these critical raw materials. And we're not even recycling them at the moment. In vast enough quantities. So what we need to really avoid is a future where we have the technological capability to address climate change problems, but these technologies that are going to do it have to start competing amongst themselves for some of these critical materials. We can't allow that to happen. We need the batteries, we need the renewables, we need the low energy technologies, lower energy use technologies such as LED lighting. We need the wind turbines. We can't end up in a scenario where they all have to fight for the same supplies. So how are we going to get around that? Well, I'll tell you about another problem first, but you can see where I'm going with this. We also have a global waste problem. We have the fastest waste stream on the planet being waste electronic materials, around 50 million tons a year, and it's increasing by about 5% a year. In the UK, we generate about 1.5 million tons per year, and the average household will generate just over 3 tons of electronic waste in a lifetime. We're going through phones, laptops, computers much quicker than we used to. We're using all this waste electronics. Another challenge is that many people store it and hoard it in their houses, and we need to get those materials back. But when we think about photovoltaics, they're not immune for this. Photovoltaics are also classified as waste electronics, of course. And by 2050, IRENA estimated that there would be 60 million tons of cumulative PV waste. Now, if you remember the graph I showed you on deployment, that was actually for one of the lower curves. If we do deploy much more, like one of the Teskey scenarios, that 60 million tons of cumulative waste becomes 100 million tons. That's a lot of waste. So this is where we need to make this renewable technology a sustainable renewable technology. The good news is that there's inherent value. They haven't been designed for recovery and remanufacture. So 94% of materials can be recovered, but it's only worth $3.50 a module. So we need to improve those things. But IRENA have estimated that 60 million tons of waste could be recycled into 2 billion new panels, which are much needed, help us accelerate deployment, generating 15 billion in total value of raw materials. And that's before we add on all of the social aspects, all of the jobs in remanufacturing, all of the increases in infrastructure we need to do that, to create those positive social aspects. And this is the thing that's around the corner for solar. We can't allow solar to be derailed in any way. So negative press around solar waste, toxic waste, a wave of waste that's going to hit us from solar. We need to think about this problem and to achieve better remanufacturing processes. Now, silicon's on the market. It has quite a well defined structure and all of these things. It's, you know, it'll take a little bit of persuasion, perhaps, to change the design of these modules for manufacturers to adapt their businesses. But for emerging technologies, we can ingrain this end-of-life thinking now. We can design our solar cells so we can take them apart at end of life, so we can extract the value materials, so we can reuse what we need to reuse. And that's an opportunity for emerging technologies. Okay, so what is needed? What's required? I've talked a lot about problems, but so what do we need to do? Well, of course, we need wide-scale deployment of affordable, sustainable green energy technologies. We need to optimize the life cycles of those technologies with maximum retention of materials. We need the design for end of life, design for circular economy. We need to avoid creating more waste. We need to avoid global resource scarcity issues, which I didn't mention, but of course, certain political players in the world are much better off in terms of the access to critical raw materials they have. So China has incredible access to critical raw materials. So politically, globally, perhaps economies will become limited by the amount of photovoltaics they could manufacture because they don't have the materials. At the same time, in the UK, we ship all of our waste electronics abroad to be treated. Why are we not treating those waste electronics, extracting the valuable materials and building green renewable technologies for them? That's what we should be doing. We need to eliminate wherever we can materials that pose risks to human health and the environment. We'll obviously talk about lead in perovskites. I think Rodrigo will talk about that a little bit later. I'll mention it in just a second, and other materials, but we need to eliminate them where possible, and we need to create jobs. And this is the opportunity. So I'm going to speed up a little bit because I think I'm just taking a bit of time from the others. But of course, in doing this, we create an opportunity to make cheaper photovoltaics. So if we design them from end of life, we can get cheaper, a lower levelized cost of electricity. The second generation panel, for example, so you put one on the market, you take it back at end of life, remanufacture using very low energy technologies. The levelized cost of energy of that second module is extremely low. That makes it economically very competitive, and this is a driver for going down this route. We'll get longer materials. We'll have materials that we can repair, upgrade, etc. We'll have reduced energy payback times. I'll finish on an example of that for perovskites. And we'll have reduced emissions. We'll have reduced carbon emissions. We'll be able to manufacture much greater volumes of photovoltaics with much lower carbon footprint. So, you know, not exacerbating the current problems we have. They'll be very competitive commercially, I believe, if we do this correctly. Okay, so now on to perovskites. Sorry, a lot of you probably came to hear about perovskites, and now I get on to talking to them. And I'm not going to talk about them in great detail. I'm going to leave that to Rodrigo and Emmanuel. But why are we interested in perovskites? Well, they offer lots of opportunities. They're very cheap, potentially cheap, low cost, manufacture, printable. We can make them over large areas. They're chemically very interesting. From a photochemical point of view, they're extremely interesting. Some might say frustrating, but very interesting. The one thing that might hold back the cost then is the encapsulation, and that might hinder end of life processes as well. We need to develop things that basically will encapsulate the device well enough so we do not leak any lead to the atmosphere or to the environment, but at end of life we can separate it and recover all of those materials. It absorbs light extremely efficiently, so it has a very high optical absorption coefficient. It has very excellent charge carrier transport abilities, long diffusion length, etc. It has a relatively high voltage. So concerns, stability, again, they'll be mentioned later in the workshop. Unstable to light, oxygen and moisture, so for a photovoltaic device, perhaps somewhat problematic, but of course, as chemists and engineers and scientists, that's just a problem that we need to address, and fantastic work is being done on improving the stability. Lead content, will it ever be acceptable? My feeling is yes, based on the current Roche directive, etc. But we'll discuss that a little bit more. Okay, as I said, very flexible in terms of material properties. So we can tune the perovskite, we can tune the layers around the perovskite, we can tune it to put it on metal, put it on glass, make them flexible, make them rigid, put them in carbon stacks and avoid things like gold. So we have lots of opportunities, and I think that's what makes them very interesting. We've done some calculations, and generally there's not fantastic resource or material resource problems down the road. So we've looked at perhaps different scenarios for deployment of perovskite photovoltaics. Excuse me. And then looked at known reserves for some of the material that we need, and it's a very low fraction of known reserves, so there's no issues there as far as we found. There may be more, some of the materials geopolitically, there may be problems down the road, and there's an excellent paper by Cadro and Hagfeldt on some of these things that I would advise you look into if you're interested. What you can see is we're going to need large amounts of solvents, and as I said earlier, I'm not going to talk about solvents today, but I will tomorrow, so they're going to be vital. And in terms of peak annual demand, so overall total reserves, fine on some of these key materials. On percentage of global production, they're not going to particularly disrupt the market, even in very high, perhaps iodine slightly in a very high scenario, but I think we've been very ambitious with what the technology will do there. So these are the challenges for perovskite. So stability is obviously a challenge, as mentioned, and again, replacing toxic materials, as mentioned, and we'll discuss that more. Large-scale manufacturing techniques, so they need to be used efficiently, and Rodrigo is going to talk through some of them later. Sustainability of devices, we need to ingrain it, and I'm talking about that a little bit now. We need to, of course, to minimize levelized cost of electricity, we need to maximize device efficiencies. Generally, as a group, we don't push for really making those, you know, world-beating efficiencies, but of course we understand the importance of doing so, and there's lots of fantastic groups around the world doing great work in doing that, but they're already very efficient materials. Okay, so that one, sustainability of devices, how do we ensure they're sustainable? Well, we need to do things like life cycle assessment. So life cycle assessment allows us to calculate the environmental impact of a material from production, so mining of materials, extraction of materials through manufacture, distribution, reuse, waste, etc. We need to decide where we draw the boundaries of our LCA, and there's metrics that need to be developed here, but generally we should make the boundary as wide as possible. What people have done quite often in the past is basically limit the boundary, and it makes products look better than they are. And indeed, governments such as the UK government has sort of, we've offset a lot of our carbon emissions by simply stopping manufacture of certain things in the UK and buying them in. We haven't really affected our carbon emissions. We just, we've put them somewhere else, or somebody else has put them somewhere else, if you like. So we need to take those things into consideration. Life cycle analysis will look at impact assessment, basically. And we have sort of midpoint categories. So that's what happens in terms of climate change from manufacturing products, how much global warming potential, how much carbon dioxide is released to the atmosphere, etc. And all of these things that might damage the environment in the short term. And then the end points. So what happens if we continue to make certain things? The end points are, you know, if we continue with climate change, there's going to be significant effects on human health, resource depletion, and ecosystem quality, for example. And what we need to do increasingly is build new metrics to include environmental LCA. As I said, that's one of the pillars of sustainability, but also to include economic drivers and social drivers. So we can choose, basically. We need flexible tools that will allow us to optimize things for the environment, but also job creation, economic opportunity, without hindering the other ones too much. And that's called life cycle sustainability assessment. And we need to, as I said, develop tools to go down this route. There has been quite a lot of work on LCA of perovskites, so I'm not going to talk too much, but there was a very nice paper on harmonization of life cycle assessment of perovskites. This table shows quite a lot of LCAs that have been carried out, and this allows us to compare a couple of things. So when we look at the impacts from perovskites, for example, of course, if you use gold, then that absolutely dominates your life cycle assessment. But let's assume that we can replace gold. That's not particularly difficult, and people have done it. with other contact layers. If we look after gold, FTO glass is a major contributor to the life cycle analysis. Gold and FTO also happen to be the two most expensive components of a device. So as I said, let's pretend, not pretend, sorry, that's the wrong word. Let's assume we can replace gold and we're left with FTO that dominates the life cycle assessment now. And what we can do about that. FTO is vital to mitigate use of ITO, indium tin oxide, because indium is incredibly critical and we can't use ITO in our devices, certainly to deploy the amount of photovoltaics that we want to deploy. So we exclusively look at FTO because we haven't got enough indium in the world to make enough solar panels to make a big impact. So why would we? And you can see here, this is a paper by Tiana and Stranks that has come out very recently. And you can see things like this is using ITO glass, and the ITO is pink, so that dominates the life cycle assessment in terms of both carbon footprint and energy consumption. And when we compare that then to FTO glass, the FTO also has a big impact. Let me just get this right. The FTO is a pale blue, so less of an impact versus. I'll have to pull that out. That's the gold contact, of course, that affects the LCA of these materials. So if you look from this point of view, we definitely want to replace ITO and not use it. You'd probably think we'd want to replace FTO glass, and we definitely need to replace gold. So we're going to run through some of them. So FTO glass. Relatively low impacts of using it, other than in terms of cost and economic cost. But also some of the studies are very misleading, because what they've done is taken the data from the EcoInvent inventory, which is one of the LCA data inventories that you can use for solar float glass. That's normal glass, or perhaps optical grade glass, but not conductive glass. Which significantly increases those impacts and embodied energy. Okay. There's other things that we need to be interested in as well and to be aware of. So to meet the projected PV demand, the world annual production of glass needs to increase by 10-fold by 2030. So glass may become not critical, but these industries need to adapt very quickly to generate the amount of glass we need to deploy the amount of photovoltaics we need. That'll probably be, this is predominantly driven by optical glass, for silicon photovoltaics. Substrate reuse there is vital from a circular economy point of view, and it's vital to replace indium. So I'll talk about that in a second. So Perovskite absorbers. So I'm not going to go into detail about whether we should use lead, but at the moment, our thoughts are there are no significant alternatives to lead that can hit the efficiencies. Tin is doing quite well, but tin has very similar problems. It's problematic. LCA studies have showed that tin has a greater impact than lead in an LCA analysis. And tin is at very high risk of supply bottlenecks, and we could exceed known reserves by 2050. And we also need it for our FTO, so it's fluorine-doped tin oxide, of course. So we need to be careful using tin. Solvents are a significant issue, and as I've mentioned several times, I'll discuss them tomorrow. So they're the two biggest, but if we look at the other materials as well, electron transport layers, again, tin, high impact, so we try to avoid tin oxide. Titania less, but very energetic in manufacture. We have to heat it to sinter it, of course, and that has considerable impact. Whole transport materials, as you can imagine, basically, we need to use simpler molecules that are easier to synthesize, that are lower cost, less energetic in manufacture. So Spiro is quite a complicated molecule to synthesize. Scale will help with things like that, but if we can look at simpler molecules, that will have a greater or a lower impact, I should say, in the life cycle analysis. Back contacts, of course, we need to move away from gold, has very high impacts, but so does platinum. Silver and carbon have lower, but they're still quite considerable, requiring the due to their deposition processes. But they're less significant overall than, say, the glass then after we've removed gold. So if we look, I've said this a few times, if you look at glass or our substrates that are available to us, if you look at glass versus something like a PET, so a plastic substrate, and others, you would say, okay, well, let's use PET because it has a lower impact than glass. But this is where we need to think about circular economy, reusing materials, recycling materials. We think we can get glass back easily enough, either mechanically or through a solvent treatment, to reuse in a new module. And there's been lots of papers on of a similar effect to this. And if we reuse it once, we can see the impact then. PET as a plastic will be incredibly difficult to get back and reuse, nigh on impossible. So if you make 2 panels with the same bit of glass, the picture changes, and now we should use glass. 3, 4. So you can see after number of product generations, glass is by far the best option. So FTO we should use, but we should look at designing modules where we can recover the FTO and use them again, minimizing the risk. And again, this paper, recent paper by the Strunks group, have shown the effect, the impact of reducing the energy payback time. So they state in their paper that recovering using recovered materials, in new modules, reduces the energy payback time by 73%. That's incredible. Most of the impacts are in the primary production of these materials, achieving a payback time of 33 days in the best case scenario, which is phenomenal. And it reduces greenhouse gas emissions by 71%. So that's to about 13.4 grams of CO2 equivalent. And that's about half of silicon. So it shows the potential of this technology if we design it for a circular economy. So I think I've spoken enough there. I'm sorry, I've taken quite a lot of time. But to summarize, we're at a crisis point. We need to innovate. We need much more research into sustainability. We have to embed sustainability into things we do. And that onus is on all of us as scientists and engineers. We need to deploy PV more quickly. And again, PV is likely to pick up the slack of other technologies. So we need to be ready to meet those surges in demand. We have to plan for end of life and develop resource efficient pathways. We can't run out of some of these critical materials. We have to design it in that we can reuse them through successive project generations. In doing so, that'll generate enormous economic opportunity, social implications, etc. So you can see how this all knits together to create a better pathway forward. Growth in electronic sector, PV sector, must be decoupled from linear consumption of materials. We need to stop digging materials out of the ground to make technologies and start recycling the ones we've already dug out of the ground. We need to view waste as a resource and adopt a circular economy. And we need to develop greater tools to guide us on these things to make sure we're not doing undue harm to any of the pillars of sustainability. So I think you've probably all heard enough from me. So I'll stop now. I'll say thank you to all of my group, all of my collaborators, all of the funders. We've done quite a lot of this work alongside the Royal Society of Chemistry. So thank you to them. I also have a position in the University of KwaZulu-Natal in South Africa. So I thank all my colleagues there. I thank you all for listening. This is a picture of elephants playing on the Zambezi River in Zambia that I took some years ago, that I like to show just because I like it. As we would say in Wales, diolch yn fawr, thank you very much. Thank you for your attention. And I'll just finish with a plug. Swansea University has done a podcast series on global problems. I've done one of these with one of my colleagues. It's in the first series, episode 6. So if you want to know more about sustainability and some of these global problems, they're quite interesting podcasts. So have a listen to. And I'll stop there and I'll hand over to Rodrigo. And hopefully I'll be back in time for some questions shortly. So if you have any questions, I'm more than happy to answer them. I hope you've all enjoyed. Yeah, thank you very much.
Well,
one example I think of often is that in the UK now we're having greater rollout of electric cars. And a lot of people on the street, what they come back with is they say, but electric cars have cobalt, they have rare materials, and these are being dug out of mines in very unfair working conditions, typically in DRC in Africa and things like this. But I think, okay, so we have this opportunity ahead of us. We have electric vehicles that are significantly better than fossil fuel vehicles in terms of the environment. So why can't we just force companies to do things the right way, to ingrain sustainability? You're saying these enormous companies with all their wealth can't produce fair working conditions for people on the ground. I mean, it should just be enforced in law, enforced by governments, and that everyone will have to do it. And of course, we can vote still then with our money and where we might purchase things from. But I think that's just a sort of a moot point, which is, you know, we should expect more of companies and governments around us as well. And
yes,
we need to hold them to account.
Yes, I'm also convinced that somehow the problems that the humanity has, like this climate change and the all other issues like migrations are also a big issue. For example, I'm from Mexico, and the Central America migration to through Mexico going to United States, that's all another issue. I mean, now all the solutions that we could propose, like for example, the use of renewable energies, somehow all these solutions are already surpassed by the problems that we are facing. But I mean, that's all a philosophical point of view. So let's start with your talk, and we can continue this discussion.
No, but I think those issues are very important for the whole circular economy.
Yes.
Exactly. I mean, just on immigration, people, we see lots of economic migrants, of course, and people are just trying to get a better life. And if we have if we see ourselves as global citizens and have better working conditions and better opportunities for people globally, then this driver for immigration is sort of removed. I think one example I use quite often is the continent of Africa at the moment is the fastest growing population on the planet. So by 2035, I believe, they will have more people of working age in Africa than the rest of the world combined. Wow. At the same time, we have opportunities to deliver distributed renewables in a green way, to create jobs, to create environmental benefit, and give people opportunities to work where they want to work and have jobs there. You know, otherwise we are going to see mass migration for climate reasons and economic reasons on a scale that we haven't seen before, I think.
Mm-hmm. Yeah, it's all interrelated. But this is a course on photovoltaics. So
yes, sorry, yes.
Did anybody else because we were going to start this second section with some questions from I don't know if there's still people that have questions from the first sessions. For Matthew. I have one question if nobody raises their hands. I was interested in your comparison of glass and PET substrates. I guess if you use a plastic substrate, all the processing temperatures are going to be lower of the fabrication, and which has a smaller carbon footprint in the end than glass. But you're mentioning basically that if you take into account recyclability, that glass is preferred. But what if you manage to recycle the glass plus FTO or the PET plus FTO as a substrate and not the separate materials?
Yes, exactly. So this comes down to the design. So things like the triple mesoporous carbon stack, for example, ideally what you would do is simply wash away the perovskite. You can decide whether you can remanufacture the perovskite or not, and then keep the entire stack if possible and just remanufacture from there. I think what we're missing, so even the example of PET versus glass versus FTO glass, I'm not saying unequivocally we should use FTO glass over PET, but what we need are the right metrics to make those decisions. So even things like when it comes to remanufacturing, some things we don't know at the moment. How much solvent can we use to dissolve the perovskite off? Because at some point it'll cost too much solvent in terms of environment to do so versus just using virgin materials. So we need those types of tools and metrics to be able to adjust them for our particular technology. So the picture will change on glass and plastic, for example, if the application changes, and we need flexibility of those systems to prioritize what we want the end result to be. But those metrics don't exist at the moment, so we need to build them. I think that's the key there.
Right, perfect. So if there's no other questions, I think we should let Rodrigo.
Yes, exactly. Just to note, I put the PDF in the chat. So if anybody has any problems opening that, just let me know, but that's there.
All right, it's there, yes. It's it looks good, yeah? Okay,
great.
So that's perfect, thank you very much. That's great. So Rodrigo, can you take it away?
Sure.
Thanks.
Yeah, thank you. Can you hear me properly?
Yes, I can see you.
Brilliant.
And hear you.
Brilliant. Can you see my slides?
It's getting there, yes.
Yeah. Is it okay?
Yes, it's also a little blurry, but.
Oh, really?
But but we can see it, yes. I mean, we can read it. It's
okay.
So it's fine. Just go ahead. Thanks.
Sorry, just to interrupt there. Perhaps what you could do, Rodrigo, is just save it as a PDF also and drop it into the chat. So if people are struggling, they can open it alongside your version.
Okay, yeah, that's a good idea.
As you go through.
I'm gonna stop sharing the screen. I'm gonna do that very quickly. Okay. So let's try that again. Okay, can you see it?
Yes.
Okay, I also sent the PDF through the chat, so it should be there. Okay, well, this is the second module of the tutorial. I'm going to be talking about perovskite materials in general, a little bit of the story of the development of the perovskite materials, and also about sort of an introduction to photoluminescence techniques to study them. So the first thing that we have to ask ourselves is why should we study perovskites? And to give a little bit of a sorry, let me just to give a little bit of an answer to that question. It's very useful to see this plot over here. You might have seen it before, but this chart pretty much shows the evolution of the efficiency of different perovskite, photovoltaic technology, and the part that I want to focus on are the orange bits right here. All of these belong to emerging technology, and as you can see here, the yellow dots belong to the increasing efficiency over the years of perovskite solar cells. And as you can see right there, the efficiency has risen up quite abruptly over the last decade. this type of increase in efficiency is unprecedented. And nowadays, it's also above like 25% efficiency. And if you compare the efficiency of perovskite solar cells with, for instance, multicrystalline silicon solar cells, which are the commercial ones, or maybe with thin-film technologies, it has actually surpassed most of them. So the perovskite solar cells have drawn a lot of attention in the scientific community, in the photovoltaic community, because of the unprecedented increase in efficiency among other things. But going a little bit to the basics, the perovskite films, the perovskite solar cells owe their name to the perovskite structure. What this means is that the perovskite structure is a crystalline structure with the formula ABX3, where A and B are cations and X, it's usually an halogen, but it could also be oxygen. For solar cell applications, the most common chemical composition of the perovskite structure is where you have an organic cation, usually methylammonium. As the cation B, you have lead, and the halogen, you usually have iodide or bromide, or maybe some sort of combination of them. If you have this configuration, you will have the structure methylammonium lead triiodide, which looks something like this. And this configuration, because of its composition, is usually referred to as the MAPI perovskite, which is sort of like the simplest one there is. But in order to understand why this material is so good to interact with light, we need to understand also the composition of sunlight, the radiation of the sun that arrives to Earth. And in this left plot right here, we can see that the sunlight that arrives to the surface of the Earth, it's actually composed of radiation of different wavelengths. In this plot right here, everything that is under 400 nanometers is what we call UV radiation. Between 400 and 800, roughly, it's what it's called the visible light. All the colors are around here in this region. And then above 800 nanometers, we have the infrared radiation. And so if we take a look to the absorbance of a typical MAPI film, of a typical perovskite film, we see that the absorption of light increases quite steeply at around 780 nanometers, which is this edge right here. This is what it's called absorption edge. And what it basically means is that this material will interact with most of the light that is 780 nanometers or has a lower wavelength. So if we take a look at this plot right here, it means that it will interact with most of the visible and UV radiation, which is actually pretty good, because that's what we want from a photovoltaic device, from a material that we want to use for photovoltaic applications. Now, this absorption edge, 780 nanometers roughly, is actually directly related with the energy band gap of the material. And now the energy band gap of the material is just the difference in energy between the valence band and the conduction band of a material. In the conduction band, our electrons are relatively free to move. And depending on this energy separation, we can actually determine the last or the ultimate voltage that we can obtain from a device made out of the material that has that energy band gap. So for instance, if we have a material with a very large band gap, we potentially will be able to produce solar cells with very high voltage, but there's also a compromise between the maximum amount of current that you can get out of that material. And actually, depending on the band gap of your material, you can calculate theoretically which is the highest efficiency that you could possibly achieve in a solar device for that material. And that is what it's called the Shockley-Queisser limit. And is this blue line right here on this plot. You can see here the maximum attainable efficiency as a function of the band gap of the material. So as you can see here, the highest efficiency for any material belongs to material that have a band gap between 1 electron volt to maybe 1.5, 1.6 electron volts. For typical MAPI films, we know that the band gap is roughly 1.6 electron volts. So it's a material that it has a band gap near to an ideal energy separation for photovoltaic applications. So the maximum theoretical efficiency for a solar device of perovskite is above 30%, which is also pretty good. But it's very important now that we know that it's a very useful material for photovoltaic applications. How are they built? How do they work? And so I'm going to show you a little bit of the components of the solar device and what's kind of like the purpose of them in the device. So we usually start with a transparent conductive oxide material, usually glass, FTO, ITO, and this material has to have high transmittance and also has to have got good conduction because we will collect charges through it. On top of it, we usually have a selective layer. In this configuration that I'm explaining right here, it's what it's called the NIP configuration, which means that you will have the electron selective layer first. But there are different configurations, and I will talk about that a little bit later. So the electron transporting layer usually is an inorganic layer. It could be a metal oxide like titanium dioxide. It's very used. It has to have a very high selectivity towards electrons. So it will collect electrons, but it shouldn't collect any other type of charge. It should also have very high transmittance because the light has to go through it. And yeah, we will use this material for charge extraction. In the Mesoporous configuration, you might have a Mesoporous layer like this one right here. Usually it's made out of the same material as the electron selective layer, but this could be different. And I will talk about that in a little bit. The original idea, because perovskite started kind of like a successor, or maybe they came after dye-sensitized solar cells, where you also have a Mesoporous layer. So the original idea was that this Mesoporous layer will have a very high surface contact with the perovskite material. And originally it was thought that this Mesoporous layer should extract the charge and then take it to the electron transport layer. So yeah, the original idea was to have a very high interface contact with the perovskite layer, that it was going to be used for charge extraction, but this is not always the case. And also because you have a Mesoporous layer and then you will have a perovskite solution infiltrated here, it can also influence the crystallinity of your material. Now, after that, we need the active layer. We need a material that interacts with light, and this is the perovskite layer. One very important thing about perovskite solar cells, one that actually makes them so versatile for so many different applications and so many different deposition techniques, as we will discuss in a little bit, is that they can be deposited through a solution process. So we can make a precursor solution and then infiltrate or spin coat this solution. And the idea of the perovskite layer is the active layer, is where charges are going to be generated. It of course should have high absorbance, that we know that it has, and it's also, as we will see, a very versatile type of material. And after that one, if you have an electron transport layer before, you need a layer that it's able to selectively take the holes or the positive charges of your device. However, because of the way we built these devices, the whole transport layer will be on top of the perovskite layer. So whatever deposition technique we use should not damage the perovskite layer. So we have to, in that way, we are going to be more limited about the type of materials that we can use. The most common for Mesoporous perovskite solar cells is the spiral metal, which is an organic molecule. And the last layer will be the metallic contact to collect charges. And that's how they look. And this is the energy diagram. On the top of these bars, we have the work function of the material, the position of the conduction band, and then on the valence band, we will have the, the bottom line right here is a valence band, the position of the valence band. And so how this solar cell works is that you shine some light. The light will go through the transparent conductive oxides, through the selective layer, and then it will hit your active material. If the light has enough energy, it will promote a charge from the valence band to the conduction band. And so you will have generated an electron and in the conduction band and a hole in the valence band. And if these bands are correctly aligned with each other, ideally the electron will move towards the electron selective layer. It will go down like this, and the hole should go to the hole selective layer. So at the end, you will collect charge. This is how a perovskite solar cell work, and this is how it's built. We of course can use different materials for the different layers, which is really good. Well, initially, as I mentioned before, the Mesoporous configuration was made out of a material that will conduct charges, but for some reason somebody thought that it would be interesting to use a Mesoporous layer of an insulating material like alumina. So in this way, there shouldn't be any charge injection into the Mesoporous layer, and so probably the solar cell built this way should not work as efficiently as the Mesoporous titanium solar cell. However, these Mesoporous alumina devices actually behave quite well, initially with an 11% efficiency, and currently have efficiencies as high as titanium dioxide. But what this configuration taught us was that the perovskite was not only capable of generating an electron and a hole, but also was capable of conducting charge, because of course there wouldn't be any injection on the alumina, so the charge will be generated in the perovskite and it will be conducted through the perovskite as well. So it can generate charge very efficiently, but it can also conduct and transport charge through the film. So someone thought, okay, so why do we need the Mesoporous structure, right? We can make only a planar device, a planar structure, and then if the perovskite layer is capable of transporting charge, then this configuration should work. And as you can imagine, it did. This is what it's called the planar structure. The advantage of this structure is that you don't really have a Mesoporous layer, so you have one less process when building a device like this. And also the first planar structure was made out of vapor deposition, which is also a different method than the one that was used before, like spin coating. So this will also give you another tool to build your devices. And nowadays, these planar structures go with efficiencies as high as 23.7%, maybe even higher. Very easy to make. And again, very efficient. And now this configuration right here is the NIP, because you will deposit an N-type semiconductor first, then the perovskite, and then a P-type semiconductor. However, you can actually revert this configuration, and you can start depositing the P-type semiconductor, then the perovskite layer, and then the electron transport layer. And this is what it's called inverted structure, or PIN structure. The advantage of this structure is that actually you can use different type of materials. So you can use metal oxides that work as hole transport layer, like nickel oxide, that is very cheap. And then you can also have different type of organic materials, or maybe electron transport layers, different to spiral that selectively collect electrons. So it opens again the window of possibilities of the types of materials that you can employ. This structure also, it's very easy to make. It's a planar structure, and they are usually made in like half a day in the lab. The efficiencies, again, are above 20% today. So again, very efficient. And there is there are different type of configurations, but these are the main ones. Along with the planar and the Mesoporous, we have the carbon cells, or the Mesoporous carbon cells. And so these type of devices are closer to the Mesoporous layer, but not quite so much. In this type of configuration, you have a Mesoporous titanium dioxide layer that you deposit via screen printing, and then you deposit an insulating Mesoporous layer. It could be zirconia or alumina, and then you have a porous carbon layer right here. And then the perovskite solution gets infiltrated into this network. And then you add some contacts on the structure. And so the advantage of this type of configuration, the carbon cell configuration, first of all, is that they can be screen printed. All this framework can be screen printed, and then you can infiltrate the solution. And screen printing is a method that can be scaled up. And also another advantage of this type of configuration is that you don't really use a whole selective layer, which tend to be a bit expensive. Instead, you use a porous carbon layer, a porous carbon matrix. And these type of cells are also quite stable. Nowadays, efficiency is above 15%. So they are very, very interesting. So the perovskite film, it's a material that is very efficient to absorb light. You have different type of configurations that you can make. But also there is another very, very interesting advantage of this material, and that is that you can actually modify the chemical composition of the perovskite film. And it's actually quite easy to do. And you can do this with different goals in mind. By changing the chemical composition, you can change the properties of your perovskite film, one of which is the band gap. So for instance, one very easy way to do it is if you start with methylammonium lead iodide, and then you start changing the iodide with bromide, you can do this via just using different concentrations in a solution. You can actually control the ultimate band gap of your material, which is something that can be very useful because depending on the uses that you want to have for your perovskite film can be very useful. And one of which, for instance, is tandem devices. So for instance, in tandem devices, you have materials with different band gaps that will interact with different parts of the solar spectrum. And so you can build kind of like a sandwich to make the most of the solar radiation. And you can build a complete tandem device with pure perovskite materials. It has been done before. For instance, in this paper right here, they got above 20% for a pure tandem perovskite device. But also another very, very interesting application is to use all the infrastructure of the silicon devices and then put a perovskite film on top of it or a perovskite cell on top of it and take advantage of the radiation that the silicon devices do not use. So you can actually create a tandem device which will be built with silicon and with perovskite. And with this idea in mind, for instance, we have this, well, we don't have, right? There's this company, Oxford PV, which builds tandem devices with silicon and perovskites. And the idea is to try to commercialize this technology. They claim to have achieved efficiencies above 28%, very, very stable devices. And so they are aiming to commercialize this type of technology. So this is one application. But then if we go back to, for instance, a typical methylammonium lead iodide configuration, because we have an organic cation in methylammonium in this network right here, this organic cation tends to be very hygroscopic. So it makes the perovskite particularly sensitive to humidity and also particularly sensitive to temperature. So we can actually get rid, or let's say not get rid, but change that organic cation with an inorganic cation. In that way, we will have a complete inorganic network. And so that's what you can also try to do with perovskites. Go all inorganic, change the organic cation for cesium, for instance, and maybe iodide or bromide. And this type of perovskite materials are actually quite resistant to humidity and quite resistant to temperature. So you will modify the properties of the perovskite by changing its composition. Cesium lead bromide is not particularly good for solar devices because it has a very large band gap. It could be used for tandem devices perhaps, but you can actually modify the bromide for iodide, and you can, for all inorganic perovskite, efficiencies as high as 18.4% have been achieved. So that's also a very good use of creativity to play a little bit with the chemical composition. And nowadays, most efficient, probably most stable perovskites are a combination of cations and anions, which have the perovskite crystalline structure. Usually you will have a combination of formamidinium, methylammonium, and cesium for the cation, and then for the halogen, you will have a combination of iodide and bromide. And you can get efficiencies very, well, above 20% with this type of configuration. And actually there is a paper, Michael Saliba, where he describes how to use triple cation perovskites, how to build them to consistently get efficiencies above 20%. It's very well described in the paper. It's not that as easy to do, but it can be done. However, regardless of that, yeah, most of the current highest efficiency perovskites are a mixture of anions and cations. Now, you also have at your disposal like a very large amount of deposition methods for the perovskite. And this is because you can actually create the precursors out of a solution. So you can start with a precursor solution of perovskite, and then you can choose whatever deposition method you need for your devices. So the most common one is the spin coating. This is a very useful technique for small scale. This is usually the technique they will use in labs. So you will take your precursor solution and spread it over your substrate, and then you will spin your substrate to get a very thin layer of your device, of your film. You can improve crystallinity with the anti-solving method, but then after the spinning, maybe 30 seconds or so, you will anneal your film, and you will obtain a very nice dark brown perovskite film. So it's very, very easy to use. It's very simple. It's what will you probably find in any lab. However, as you can figure, it's quite wasteful because most of the solution will just spin out of the film. But there are different methods at your disposition, particularly because you can start with precursor solutions. These methods include chemical vapor deposition, slot die, which is great for scaling up roll to roll. I will talk about some of these techniques later. Blade coating and screen printing. So all of them deposition techniques that you can use for perovskites. Now, this is kind of like the general information about perovskite solar cells, their versatility, what you can do with them. But to improve any technology, we need to understand a little bit better what's going on inside of them, the internal mechanisms. So if we take a closer look to the perovskite solar cell, we see that there are a lot of processes that can be happening whenever our material is absorbing light. And here are some of them. I will talk a little bit about some of these later today, but so for instance, if your material is absorbing light, the first process that will happen is absorption of light. This will create an excited electron, and this absorption process happens really fast in femtoseconds. And then what happens is the internal conversion. This electron relaxes to a low energy vibrational level. I will talk about a little bit about that later. This is called internal conversion. It also happens really fast in a picoseconds scale. And then you can have charge injection. If you have one electronic charge right here, it could be injected into your Mesoporous layer, or maybe the selective material as well. This process also happens really fast in nanoseconds. You can also have charge diffusion. Let's imagine that we have a planar device, then the charge will have to diffuse through the perovskite film, or maybe through the Mesoporous layer. You can have recombination. So the electron might recombinate with the hole that left behind. And this recombination can be radiative. That is the emission of light after recombination. This is also a very quick process, 10 to the minus 8 seconds. But also you can have trapping. Maybe your film has a lot of defects. Maybe on your surface you have a lot of defects. So this electron might get trapped and then ultimately recombine without any radiation emission. This is also a process that can happen really fast, in the order of nanoseconds. But you can also have surface recombination. So let's say that you have injection, but maybe the transport is not very efficient. So this electron might recombine with holes that you left behind on your film. So these are very, very complex process, very, very fast process. And we need to understand a little bit more about them in order to suggest improvements. And I'm going to try to explain a little bit, well, both me and Dr. Emmanuel Pean, about how you can use photoluminescence techniques, photochemical characterization to study these methods. But before that, I want to explain to you a little bit about what it is, what's photoluminescence. And so to understand photoluminescence in this particular slide right here, we have two states, the ground state, which is this curve right here with S0, and the excited state, which will be this one right here with S1. Each one of these states has these lines. These are vibrational levels of different energy right here. And so when you shine some light onto your material with enough energy, absorption will happen. And what this means is that your charge will jump from the ground state to an excited state, S1, probably to a vibrational level that is not the lowest one in energy, but maybe to a higher energy, a higher vibrational energy. This process happens again very, very fast, 10 to the minus 15 seconds. And then once you have your charge right there in the excited vibrational level, it will relax. It will relax to a lower energy vibrational level. This is what it's called internal conversion. This process happens really quickly in the order of picoseconds. And then once you have your charge in the lowest vibrational level, it can recombine again. It can return to the ground state. And if photoluminescence happens, this recombination will emit a photon of light. This process is on the order of 10 to the minus 8 seconds. So it's in the order of nanoseconds. And now one really interesting thing to see here is that the radiation of your photon usually happens from the low energy vibrational level, probably to a high energy vibrational level in the ground state, or maybe not even there. But this photon of radiation, of fluorescent radiation, is of lower energy than the photon that you use for absorption. And this is what it's called Stokes Shift. And so one really nice example of it is the tonic water, which has quinine or quinine. And so if you radiate UV light, which has a lot of energy, the bottle will actually, well, the tonic water will shine with a very nice blue light. So you use UV light, but the radiation is blue. And some other examples of fluorescent materials are rhodamine and fluorescein that can be sometimes in antifreezing liquids. And this is what overall the photoluminescence process. However, in the lab, we use we use this process to study materials. And what I'm going to describe right now is how a steady state photoluminescence experiment happened and how to present the data. So in a photoluminescence, steady state photoluminescence experiment, what you have, it's you shine some light, white light if you like. Then you use a filter or a monochromator to select whatever wavelength you want to use as the excitation wavelength. And then in this case, blue, it will hit your material. If you have photoluminescence, if you have emissions of photons, the emission of photon of your material will happen. This light will have less energy than the excitation light that you use. This is the emission light. And then it will be detected. Once you detect the emission, you can actually take your data and you will present it like a plot, in a plot like this one right here, where you will plot the intensity of the emission against the wavelength of the emission. This is usually how would you present the steady state photoluminescence information. Now, this is the experiment, but what information can provide? So again, let's take a perovskite material right here. We shine some light on a perovskite film. This film is in an insulating material, probably a piece of glass. So we excite a particle right here with light. Now the charge might not have anywhere to go, so it will eventually recombine again with the hole that it produced. And depending on the energy separation between, in this case, your conduction and your valence band, you will irradiate some light This is what it's called a radiative recombination, whenever you have recombination and you emit a photon. But the energy of the emitted light, it will depend on the energy separation of these bands. So actually you can have different compositions of your perovskite with different band gaps. And so the emission of the light on this experiment will be different depending on the band gap of your material. So with this type of experiment, you can actually have a rough idea of where the band gap of your material is, which is very, very interesting. This is for quantum dots. And as you can see, depending on the perovskite composition, you will have different emission light. Now, you can also use the intensity of photoluminescence to get a little bit more information. So for instance, let's say that we have talked about the radiative recombination. However, the perovskite field might have a lot of defects, might have a lot of surface states, a lot of grain boundaries. This type of positions will make that your charge might be trapped in some of these states. And then the process of recombination through here will be non-radiative. That means it will you will lose the electron, but you won't observe any sort of radiation out of it. So you can actually, of course, this will decrease the intensity of the emission, the intensity of illumination. So depending on the maybe of the crystallinity of your sample, maybe on the purity of your sample, maybe on the defects that you have, the intensity of your photoluminescence will change. So this can actually give you information about the radiative recombination that you have, but also the non-radiative recombination that you have. For solar devices, for LEDs, you want to maximize the radiative recombination against non-radiative recombination, and that is because you will have a lot of trap states that you don't really want because you can lose charge in that regard. However, for a steady state experiment, this can be, visually interesting, but we need to help them a little bit. And in order to do that, we use an integrating sphere to obtain the photoluminescence quantum yield. And the photoluminescence quantum yield, what it is that it tells you of the amount of photons your sample is absorbing, how many of them are being emitted. That is, let's say that 100 photons are being absorbed, I'm emitting 50% of them. That means that 50% is radiative recombination, 50% is non-radiative recombination. The way it does it is that you pretty much put your sample in an integrating sphere. And when you have an integrating sphere, whenever you put some light inside of it, it will bounce out of the walls until eventually it will get to the detector. So if you put that sample right there and you put an excitation light source, you can actually know how much light is being absorbed by your sample, depending on the decrease in intensity of the excitation light. But also your sample will emit some photons. You will have emission out of your sample, and you can actually know how much emission you have. So you will know exactly how many photons are being absorbed and how many of them are being emitted. And that will give you a lot of information about radiative and non-radiative recombination. So it's a very nice supplementary technique for steady state photoluminescence. Now, this type of experiments, steady state photoluminescence, can also be very useful to evaluate the quenching capability or their charge extraction capability of different materials. So let's imagine again the experiment. So if we have, for instance, a perovskite and we have generated an electron charge, we have this perovskite material on top of a selective layer. If it's a very good one, whatever charge we are generating will migrate and will go to the selective layer, like in this diagram right here. So we're generating charge. If it's a very good selective layer, it will take the charge, and then the charge will have nowhere to go. We will accumulate on the surface and then will ultimately recombine. But what we're doing right here is actually reducing the radiative recombination and transform it to non-radiative recombination. That is, if you have a material that is very good quencher, that is very good material for selecting charges or extracting charges, the radiative recombination will decrease, and that implies a reduction on the intensity of photoluminescence. In this diagram right here, it was an experiment that I did, was using titanium dioxide only with a planar configuration like this and a Mesoporous layer, which will be like a very large interface between the perovskite and the titanium dioxide. And as you can see that when you use a Mesoporous layer, the quenching is so high because you have that interaction. So this technique can be quite useful to evaluate charge extracting layers. However, a reduction in photoluminescence intensity might be due to very nice quenching capabilities of the material, or might be just because you're just creating a lot of trap states on the interface. That can be another reason why the intensity will drop. That is why you might use electroluminescence techniques to complement these measurements as well. And so in electroluminescence, what you do is you have a complete device and you make it work backwards. So instead of taking charge out of it, you inject charge and drive it towards the selective layer, towards the active layer. So effectively, you will inject chargers into your perovskite and will promote radiative recombination or non-radiative recombination. And so what this process can do is actually tells you if, for instance, in this experiment right here, they use different materials as quenching materials, and then they measure the intensity of electroluminescence. And they actually were able to find out that the decrease in photoluminescence intensity when they use this material was actually due to charge extraction, because when they injected charges into the film, the intensity of the electroluminescence increased, and that is radiative recombination right there. Another technique very useful to study photoluminescence is fluorescence microscopy. It's actually quite nice. What you do is, again, you take a little bit of light, you select whatever wavelength you need with a filter, and then you shine this light to your sample. The photoluminescence of the sample will go through the detector. And so, for instance, these are methylammonium lead bromide crystals. These emit in 540 nanometers light, and usually the red ones could be, for instance, methylammonium lead iodide, which shines around 775, 780 nanometers. So this is, and you can actually study this over time, which is quite useful. Now, these are the descriptions of the techniques, but we also need to consider how the measurements should be done, what can happen while we're measuring our sample. So I'm going to explain a little bit about changes of photoluminescence over time. So let's try to think again about what's going on whenever we shine some light on a perovskite material. So we have excited our electron right here, and now the electron can recombine through a radiative recombination, or might get trapped and lead to a non-radiative recombination. But if we continue shining light into our sample, what's going to happen is that well, three things might happen. And the first one is that these electrons right here, because the perovskite film is made out of the solution process, you probably will have a lot of defects, a lot of vacancies. And some of these vacancies are iodide vacancies, which will have a positive charge. So these will attract the electrons. The electrons will go through these iodide vacancies right there, and then it will start filling these traps made out of iodide vacancies. And then the iodide that you have on your sample will migrate away from there, and then it will start to passivate other traps that you have in your crystal. So if you continue shining light and sending electrons to the conduction band, these electrons will get trapped and will passivate these traps. And so eventually what will happen is that you will reduce non-radiative recombination through these traps. Now, another thing that can happen, or that will happen simultaneously, is that if you have electrons there and then you have a presence of oxygen, you can actually create what is called superoxide. And these superoxides, O2 plus the electron, will also like to passivate these iodide vacancy traps. So again, you will be passivating traps with the superoxide, and this will reduce the non-radiative recombination. And if you have presence of water, you can also dissolve a little bit about this perovskite film, and a lot of these surface traps will be removed. And again, you will be reducing the non-radiative recombination. So all these three processes, what we'll do is that they will make that if you have a sample and you measure it over and over and over again, the intensity of your photoluminescence of your material will, the intensity of your photoluminescence will increase over time. This is what it's called photobrightening. But if you keep exposing your sample through light, the same oxygen that created the superoxide and passivated some of these traps will start to degrade the film. And the same with water. The perovskite is not very stable with water, particularly in presence of oxygen. So you will start to lose your perovskite film. So you will have degradation. And this degradation will reduce your radiative recombination. And so the intensity of the photoluminescence will decrease over time. This is what it's called photodarkening. It's related with degradation of the samples. So in the work of Dr. Emmanuel Penn that we'll talk in a little bit, he showed actually that the intensity of photoluminescence will change over time, but it will change differently depending if you have an air atmosphere or nitrogen atmosphere. So if you have an air atmosphere, yeah, you will have a very, very quick photobrightening because you will have all of these three processes at the same time. But this will lead ultimately to degradation of your film. So eventually it will lead to photodarkening. But if you have a nitrogen atmosphere, you will only have some of these trap fillings, but no degradation. So the intensity will increase because you're reducing non-radiative recombination, but you won't have any presence of oxygen or oxygen and water. So you won't have photodarkening. And another very interesting result of this experiment, of this project, was that as time goes by, the MAPI peak on XRD will decrease over time. The lead iodide formation will start to appear. So that means degradation. And in this plot right here, we see the evolution of intensity over time. And as you can see here, the sample starts photobrightening over time, but at the same time, you have formation of lead iodide right here. So it means that even though you have photobrightening, you also have degradation. Both processes happen at the same time. So even if you think that your sample is getting better and better with photoluminescence, it might also mean that photodegradation is taking place. So it's something to keep in mind. And this is a very nice experiment with the photoluminescence microscope. On the left, you see the evolution of the photoluminescence over time with the fluorescence microscope. And on the right, you see the evolution of intensity of illumination. So as you can see, you see photobrightening first, and then degradation happens, and then you have a decrease in the intensity of photoluminescence. Another good example of how to use fluorescence microscopy there. So there are some advices, good practices whenever we're using steady state photoluminescence. And some of them are very common sense, right? So if you want to compare between samples, you have to use the same substrate. You need to use the same conditions. If you can, you need to encapsulate your material to prevent any type of degradation. Also, if you want to compare between materials or maybe the same sample, but you want to compare intensity because you're doing something different, you have to follow the photoluminescence until it reaches a steady value right here. And then you can compare the intensity of photoluminescence at that point. Or you can follow the evolution of the intensity of the photoluminescence if you want to compare between samples. And also, if you can, try to measure under inert atmosphere. Now, this was a little bit about steady state. I'm just gonna explain a little bit about time resolve techniques, time-dependent characterization techniques. Today, we're gonna talk about time resolve photoluminescence. We're not gonna talk about transient absorption spectroscopy, but I will talk a little bit about that in my presentation tomorrow, so you're welcome to join. But I'm just gonna explain very quickly time resolve photoluminescence. I'm just gonna explain the experiment, and then I will give the presentation to Dr. Emmanuel Pean. And in this type of experiment, what we do is we take a very, very quick pulse of light and we shine it over our sample. We register whenever this pulse of light arrives to our detector. And then our sample will eventually emit a photon, and we compare the arrival time of this emission of this photon against the light, the time where we shine some light on our sample. So this will give you a time difference between these two processes. Now, in this type of experiment, what you do is you will count only one photon of this experiment, and you will repeat the experiment over and over and over and over again. And you will create a histogram of the time of arrival of the emitted photon, like this. This will eventually give you the decay profile of the emission of your sample. And so the idea here is that you can actually measure very, very short and very, very quick emission of your sample in a very small time scale. And so you can get an idea, a very, very quick process that happened inside your sample. Follow pretty much the evolution of photoluminescence over time, but very, very short periods of time. Dr. Emmanuel Pean will talk a little bit more about the details of this technique. But yeah, the idea is to be able to follow the decay of the photoluminescence of your sample. With this slide, I will give, well, that's it for me for this second module. And now I will stop sharing my screen to give time to Emmanuel to present his. I don't know if should we have any questions, or maybe we can go through the next module.
Well, let's quickly check if there's any questions. Rodrigo, you stick around for the rest of the sessions as well, right? Or
I do. Yeah.
Okay.
Yeah, I'm gonna give the fourth module as well.
Okay. So any questions now, anybody? Raise your hands. If not, then Emmanuel can.
Yeah, I have a question. Rodrigo, as you said about the, to be precise about how we measure the photoluminescence. One thing is, you said that the perovskite may have defect and pinholes and those things. So about one sample, how you measure that? You put the sample in different zones and then you make average spectra of the different zones, or just one zone and that's it? Because I guess maybe it has some difference.
Yeah. So what I usually do, you can actually try to scan different regions of your sample if you like. But what I usually do if I'm making something different is to make several samples of whatever I'm changing, and then let me share you the screen really quickly. I don't know if you can see here, for instance, but it really depends on what you're trying to study. What you can do that, but that would be only one sample, right? And you know that between sample and sample, there might be some difference. So what I usually do is I usually take at least 3 different type of the same configuration sample. So if I'm using a MAPI, I will make like 6 films or something like that, and I will measure each one of them until they reach the steady state photoluminescence. And then I will measure them, and then I will take an average value or of the photoluminescence. I don't know, you can see it right here, for instance, that you have a line in the middle, but then you have a dispersion. And that is because you will have differences between samples, right? And you want to register that one. If you compare only one point of only one sample, that could be anything, that could be anywhere. But if you want to give a little bit more of statistical significance to your measurement, what I would recommend you to do is to make several samples and then measure photoluminescence to all of them, and then see how it looks. And also what I usually do for photoluminescence measurements, particularly for perovskites, is to encapsulate them with PMMA, which is an encapsulated material, very cheap to use, very easy to deposit. And that will actually protect your sample a little bit longer, particularly from oxygen and humidity. So that will definitely help to have more stable photoluminescence measurements as well.
Okay, and another quick question is about the reference that you use. For example, in some of those graphs that I saw in your presentation, you have like glass plus MAPI as reference. But when you have like Mesoporous films, do you think that maybe you should have some zirconia layer or something like that, or how it works? Okay, yeah. I remember for dye cells, I used to do like that, but I don't know how it works here.
Yeah, so the problem with, let's say that you have a Mesoporous layer, let's say that you have titania and you want to measure photoluminescence, it's gonna be very challenging because these type of materials, particularly Mesoporous titania, will interfere with the photoluminescence process. You will have a lot of quenching. So I think it will be very hard to get a lot of useful information from there. I think photoluminescence is very useful if you want to study the film, if you want to study the crystal. It will be completely different. For instance, if you use an insulating material like alumina or zirconia, and you measure photoluminescence, the photoluminescence will be very high, but it will have nothing to do perhaps with the type of recombination that you will have or the type of behavior that you will have with a Mesoporous titania layer, because just the properties of the materials are different. So if you try to measure photoluminescence with a titanium dioxide Mesoporous layer, it's going to be very challenging because you will have a lot of quenching. So it really depends on what you want to prove or what you want to show in that regard. I will recommend you, if you want to study photoluminescence, if you're doing something to your perovskite layer, maybe just a perovskite film on glass. If you need to use a semiconductive layer, then it will be a little bit more challenging, and then you have to think about really what you want to study. But that's the problem.
Okay, yeah. Thank you.
May I make a question? Yes,
Rodrigo, do you notice some polarization effects in your measurements, in your PL measurements?
Yeah, I guess. I mean, you can also have that, but I with perovskites usually it's quite straightforward. You don't really see something out of there, but you can have that. You can study that as well. It's just something that I haven't really done a lot. Well, not I haven't done really, but it doesn't really interfere a lot with this type of steady state measurements for perovskites at least.
Yes. Okay. Thanks. All right. So thank you very much, Rodrigo. Let's continue with the next module, and we'll see you a little bit later.
Yes.
All right, can everyone hear me?
Yes, sounds great. And your slide looks good. So
perfect. All right. That's fine. Sorry, having some technical problems. All right, so I'm Emmanuel Péan. I'm a postdoc in Maths Group. I've finished my PhD about a year ago, and the focus of my PhD was photo brightening and photo darkening, including some of the work that Rodrigo just presented. Then I did some study on superoxide formation in Mesoporous perovskite solar cells, which I think Matt talked about. And finally, I looked at how we can interpret steady state and time resolved photoluminescence of perovskite materials, which is the subject of my talk today. So just a quick reminder on photoluminescence, which I'm sure Rodrigo talked about before. So just very quickly. So when light is absorbed by your material, a ground state electron is going to be excited into an excited state. Now, depending on how the electron is going to go back to the ground state, you are going to have fluorescence or phosphorescence, but in general, it's photoluminescence. Now, this is in a molecule where you have discretized energy levels. In a semiconductor, such as perovskites, you have so many energy levels, so many atoms, that they are going to form an almost continuous energy band. And the last band occupied by electrons at the OK is going to be the valence band, and the first band non-occupied by electrons or occupied by holes is going to be the conduction band. And the energy difference between the two is the band gap energy. So nothing fancy here. Right, so to characterize perovskites or materials in general, usually there are two types of measurements, of PL measurements. First is steady state PL, which is basically a measurement of the sample in the steady states, which means that the sample does not change over time. Usually this is achieved by continuously illuminating your sample. So I'm sure everyone is common with emission or excitation spectra, where the so for emission spectrum, you are going to keep the excitation wavelengths fixed. So for example, let's say 450 nanometers, and you're going to record the emission spectrum between over a range of wavelengths. So here, for example, this is the emission of, I believe, a MAPI thin film, which emits at about 760 nanometers. And then you've got excitation spectrum, where instead of changing the emission wavelengths, you change the excitation wavelengths, and you look at the emission wavelength at one emission wavelength. Then you've got time resolved photoluminescence. Just need to move that. There you go. So time resolved photoluminescence, you are going to look at the photoluminescence of the sample, but in a transient state. So when the variable of the system, we'll see that later, are still changing. So it's before the steady state. And this is usually achieved by exciting your sample with a very short excitation pulse instead of a continuous excitation. And obviously a very good example of time resolved PL is, well, time resolved PL, which is this, which looks like this. So usually a decay of the PL intensity over time, where your excitation and emission wavelengths are fixed. All right, so the question I'm going to try to answer today is how or what information can be extracted from steady state and time resolved PL. Right, so to answer that question, we need to look at what recombination processes are happening in perovskite materials. So let's say we excited a certain amount of electrons, so Ne electrons, and we are going to have, therefore, N holes in our valence band. Now, because of the very low exciton binding energy in some perovskites, such as methylammonium lead iodide, MAPI, recombinations are termed bimolecular. So for example, band-to-band recombination, which is a direct recombination of an electron in the conduction band with a hole in the valence band, which is a radiative process, is a bimolecular process of rate constant Kr. And thus, if we look at the variation of the electron and hole concentration over a small period of time, here, over this small period of time dt, we are going to lose an amount of electrons and holes equal to Kr, so the radiative recombination rate constant, multiplied by the electron concentration, multiplied by the hole concentration. So you can see it's a bimolecular process. It requires two carriers to happen, hence why we have both the electron and hole concentration in the equation. And obviously, since we are losing electrons, we are going to have the minus sign in front of it. And as I said, it's a radiative process, which means that you are going to emit photons during this process. Now, there is a phenomenon called photon reabsorption or photon recycling in some materials, including perovskite. And this usually happens when the Stokes shift between the PL emission and the absorption is small. So when the absorption and the PL overlap, because then the photons that have been emitted can be reabsorbed by the material. So when we look at the emitted number of photons, we need to add a constant eta escape, which corresponds to the escape probability of a photon. Therefore, the PL intensity that we are going to measure when looking at steady state or time result photoluminescence is going to be equal to the escape probability multiplied by the bimolecular recombination, the radiative recombination rate, which is Kr, Ne, Nh. So what about the remaining photons which are being reabsorbed? So this is going to be 1 minus eta escape photons reabsorbed. So we can add this term to our equation, which is here, which is basically 1 minus eta escape multiplied by the radiative recombination rate. We can do that because the absorption process is really much, much faster than the bimolecular, the band-to-band recombination rate. Now there's one last bimolecular recombination process, and that's a non-radiative process, which is believed to be caused by either trapped assist OJ recombinations or shallow trap state mediated. And like for the band-to-band recombination process, its equation is going to be simply Kn, Ne, Nh. And you can see that everything depends on Ne and H in this equation, which means that we can simplify it as eta escape Kr plus Kn, and then multiply by the carrier concentrations. And because usually we can't tell eta escape Kn and Kr, since they both depend, well, they all depend on Ne and H, we usually sum it up as the bimolecular recombination rate, Kb. Right, so what about trap-mediated recombinations? We know that trap states are a big problem because they usually mediate non-radiative recombination, and they're usually pretty fast, which means that they are detrimental to device operation as they prevent the carriers from being extracted into the ETL and HTL. So again, any electrons in your conduction band, NH in the valence band, NH holes in the valence band. So there is two ways to consider trapping and detrapping. So the first way is a bit complicated, but it can be considered as the bimolecular process between the excited electrons, so or Ne, and the available trap state. So the total number of trap states here is big NT, and the trapped electrons is small nt. So the available trap state is going to be the difference between available and occupied. And this is going to happen at rate constant kT. So again, if we look at our rate equation, so I really need to get the Zoom stuff out of the way. I can't see my presentation. Oh, I can't select the focus anymore. Oh, here we go. Perfect. So yeah, if we look at our rate equations, so these variations or the carrier concentration over time, so we've got variation of electrons, holes, and trapped electrons. We are going to lose an amount of electrons equal to the trapping rate constant multiplied by the electron concentration multiplied by the available trap state concentration. And therefore, we are also going to we are going to increase our trapped electron concentration by the same amount. And then we've got detrapping, which is very similar, is a bimolecular process between our trapped electrons and our available holes. So then it's going to be the detrapping rate constant multiplied by the trapped electron multiplied by the hole concentration. Going to decrease our hole concentration and going to decrease our trapped electron concentration. So yeah, it's pretty complicated. There is a way to simplify about this, but it's based on big assumptions. So if we assume that the trap state concentration is high enough, or if the detrapping rate is the detrapping rate constant is high, then we can assume that the trapped electron concentration is negligible compared to the electron and hole concentration. And in this case, we can consider trapping and detrapping as monomolecular processes. And as you can guess, monomolecular indicates that the rate of this process only depends on one carrier concentration. And indeed, you can see that the electron and hole concentration in this model are going to decrease by an amount equal to the trapping rate concentration, the trapping rate constant multiplied by the electron concentration. So much, much more simple. Right. I'm going to talk about OJ recombination and injection here, but I will not include it in the rest of the talk. And I'm going to explain why now. So OJ recombinations are a trimolecular process, which only happens at very, very high excitation fluorescences. That's why it's usually ignored. Also, it's been found that the OJ recombination rate in perovskites is very small, or it's believed to be small. So it's usually ignored. So OJ recombinations happen when the recombination of an electron with a hole in the valence band, the energy released by such recombination is going to be captured by an excited electron, which is going to be further excited. So as I was saying, trimolecular process, which means that the rate of this process is going to be equal to the OJ recombination rate constant multiplied by the electron concentration squared multiplied by the hole, since we need 2 electrons to happen plus 1 hole, so trimolecular. Injection can be easy to model, considering that it's technically a monomolecular process, which obviously is going to happen only if you have an ETL or HTL. It's a monomolecular process because it only requires one carrier to happen. So you've got your perovskite here, and then you've got your ETL. So you've got your conduction band of your perovskite is obviously higher energy than in the ETL. So there will be a electric field, which is going to drive the electrons into your ETL. Now, the problem is that usually we know that the electron mobility in perovskite is pretty high, and sometimes a bit higher than in the ETL. So what's going to happen is that your electrons are going to move towards the interface, go into the ETL, and then not move because they are much, much slower in the ETL, which means that you will have a buildup of electrons at the interface and holes here, which so there will be a charge concentration gradient. And this charge concentration, sorry, forgot to say, so monomolecular process, obviously proportional to the electron concentration multiplied by the injection rate constant. Going back to the concentration gradient, which means that you will have this concentration gradient, which is going to force the electrons to go back or to recombine in the perovskite. And this adds a layer of complexity to the thing, because this concentration gradient, or the electric field created by the concentration gradient, is going to be dependent upon time. So all the rate constant for injection is going to be dependent upon time, which makes things much, much more complicated. But to keep things simple here, I'm going to consider a sample which is just a MAPI thin film deposited on glass. So there won't be any injection, and I'm going to ignore orgy recombinations, although I could have talked about them. It's not adding too much complexity, not as much as injection. Right, so here I'm going to talk about two models. And the first one is the bimolecular trapping, detrapping, or BTD model. So in this model, we're going to consider everything, well, everything, sorry. We're going to consider two of the processes I discussed before. So bimolecular recombinations and trapping and detrapping as bimolecular processes. We're also going to consider that the material is a p-type sample, which means that you will have p0 dark holes, and therefore the total carrier concentration is going to be Ne is equal to delta Ne, where delta is the photoexcited carrier concentration. So the number of carriers you excited with your light through light absorption, and NH is going to be the photoexcited hole concentration plus the dark hole concentration. And therefore, we can construct our rate equations using the previous rate equations. So it looks a bit complicated, but don't worry, it's not that bad. So the variation of the electron concentration over time is going to be, the electron concentration over time is going to decrease due to bimolecular recombinations here, and also trapping. The trapped electron concentration is going to increase through trapping and decrease because of detrapping. And finally, the hole concentration is going to decrease because of bimolecular recombinations and detrapping. And this is some of the values retrieved from the literature for the different rate constant. Now, the second model I'm going to discuss is much more simple because we are going to assume that our trap states are going to remain mostly empty at all time, which allows us to use the monomolecular version of the trap state mediated recombination. Now, if we also assume that we don't have any doping, then we can just say that the electron and hole concentration, it should be an H here, sorry. The electron and hole concentration are both equal to our photoexcited carrier concentration, and we can just simply note it N. And in this case, the rate equation is simply, and it's very simple, where the the carrier concentration is going to lose carriers due to bimolecular recombinations and trapping. So an extremely easy differential equation. And this is some of the values retrieved in the literature for KB and KT. Right, I'm pretty sure you are very tired of seeing so many mathematical equations. So I'm going to show you some very nice graph now. And I'm going to start talking about time-resolved photoluminescence. Oh, sorry, I thought there's a bit more equations, but I'm done soon, don't worry. So time-resolved photoluminescence, Rodrigo talked about it, usually carried by exciting your sample with a very short excitation pulse, which is going to generate and not carriers and not electrons and holes in your sample. And then you monitor the photoluminescence just after this excitation pulse. So you can simulate time resolved photoluminescence by numerically solving the rate equation of the BT and BTD model using the initial condition, which is that the photoexcited electron concentration, so at time 0, when you excite, and the photoexcited hole concentration is equal to N0, which can be calculated from your laser fluence in photons per centimeter square, your sample absorptance in %, and your sample thickness in centimeter, which give you a value per centimeter cube. And then once you simulate your TRPL, you can fit your experimentally measured TRPL, which allows you to retrieve all of your parameters such as KB, KNT, KD, and so on. So it's pretty neat. Well, we'll see that in a minute. Just a quick note, it's not very important, but I'm going to talk about the contribution of the processes. So how much each process, so the bimolecular process, the trapping process, the detrapping process, are going to contribute to recombinations in the sample. And this is a good way to estimate, well, this is a good way to get information. And the contribution is basically a fancy word I'm using for basically the process rate. So for example, for the BT model, the bimolecular contribution, so how many carriers are recombining through bimolecular recombinations, is going to be equal to KBN square, and the trapping contribution is going to be KTN. Similarly, for the BTD model, the contributions are going to be as follows. Now, what we are measuring when we are measuring TRPL is not the carrier concentration. We're not looking at the carrier concentration. We are looking at the TRPL. So we are not interested in knowing how many, we're not interested in knowing the bimolecular or trapping contribution to the carrier concentration. We want to know how much bimolecular recombination and trapping and detrapping are affecting our TRPL. So, which is what I wrote. So basically, instead, we are going to calculate these things, which are basically calculated from the variation of the TRPL over time. There's no need to go through these equations, but just so you know, we are looking at the contribution of the recombination processes to the TRPL change. Right, some actual graph. I'm sure you're very excited to see what we can get with these models. So first, I'm going to discuss the fluence dependence of the BT model. So if we change, so we're going to change our fluence by changing our value of N0, so how much carriers are being cited. So we start at low fluence, so 10 to the power 14 to multiply by 10 to the power 15. And you can see in this regime, trapping is the dominant process where bimolecular recombinations are negligible. And this is because in here, KBN square is going to be much lower than KTN. So most of your carriers are going to undergo trapping. And because your rate equation can be easily simplified as dN over dt is equal to KTN, your TRPL decay is going to be mono-exponential. As you can see on the log scale, it's a straight line. And in this regime, the shape of the TRPL decay will not depend upon the excitation fluence. Now, if we increase our excitation fluence, you see that bimolecular recombinations are starting to become non-negligible because KBN square starts becoming above the same as KTN in terms of intensity. So you've got both trapping and bimolecular recombination happening. And in this regime, you can see that the TRPL intensity, TRPL decay, is going to depend upon the fluence, the excitation fluence. And as you would expect, if we increase further the excitation fluence, then bimolecular recombination are becoming dominant and trapping becomes negligible. And although you can't see it here, but the TRPL decay shape still depends upon the excitation fluence. So what's the takeaway here? Well, trapping dominant at low fluence, bimolecular recombination dominant at high fluence, and then in the middle, we've got a mix of both. And if you were to measure TRPL, and so mono-exponential decay, whose shape is independent on the excitation fluence, then that probably means that your sample is in the low fluence regime. So I forgot what was my slide there. So now let's talk about fitting. How can we use this model to fit data? So to investigate that, what I did is that I simulated some TRPL decay using the BT model. And then I sprinkled a bit of noise on top of it to simulate experimental data. And you can see that my simulated with noise is pretty similar to my experimental data, so not too bad. And what I did then is that I used a BT model to fit the simulated data with noise, which seems pretty dumb, right? But actually, maybe not so dumb. And then I looked at the value of KT and KB I retrieved from the fit, and I compared it to the one I used for the simulations. So let's have a look. In the low fluence regime, we can see that we are retrieving perfectly KT, but KB is not retrieved accurately. And this is because in the low fluence regime, you don't have any bimolecular recombinations. So how can the model fit something that does not exist, right? So that's why you won't be able to accurately retrieve KB. Only in the medium fluence regime, you will be able to retrieve both KB and KT because both processes are non-negligible. And as you would expect, if you go in the high fluence regime, you will be able to retrieve KB accurately because bimolecular recombinations are dominant, but not KT because trapping is negligible. Now, this is a problem because when you're going to do your fitting on your sample, you're going to get a value of KT and KB, but how can you make sure that these are correct? Because instead of, in my case, I know what values are used, right? So I know when they're correct or not, but you won't be able to tell if they are correct. And there's a very easy way to ensure that the values you retrieved are correct. You simply need to calculate the contributions of the different processes using the value you retrieved from the fit. So you can see that when the bimolecular contribution calculated from the fit goes towards 0, so you can see that the bimolecular recombination rate becomes inaccurate. And as well, when the trapping contribution tends towards 0, your trapping rate becomes inaccurate. Right, so an easy way to ensure that the trapping and bimolecular recombination rate that you have retrieved from fitting are accurate is to simply calculate the contribution and just make sure that they are not very low. So obviously the perfect case would be 50% trapping bimolecular. What's interesting also is that if we change the amount of noise we add to our simulation here, you can see that the range of excitation fluences where we can accurately retrieve both KB and KT is going to decrease, which makes sense because noise is going to be removing information from your data. So obviously less noise, better data, nothing new here. Right, the BTD model is a tad more complicated compared to the BT model, as you can guess from the look of the differential equations, but it's not too complicated. So as for the BT model, in the low fluence regime, bimolecular and detrapping are going to be negligible, while trapping is going to be the dominant process, which means that, again, the TRPL decay predicted by this model is going to be mono-exponential, and its shape is not going to depend upon the excitation fluence. As well, in the high fluence regime, bimolecular recombinations are going to be dominant, while trapping and detrapping are going to be negligible, as you are going to saturate your trap states. So most carriers are going to undergo bimolecular recombination at this point. Again, we'll have fast recombinations, which whose TRPL decay shape will depend upon the excitation fluence. It's in the medium fluence regime that the BTD model is going to is going to be different from the BT model, because here we've got detrapping, but you can see that detrapping is going to be fairly, or the contribution of detrapping is going to be fairly limited in terms of how much it affects the TRPL decay. And you can see that the shape of the TRPL decay in this regime is a bit weird, at the least to say. But there is a very easy way to analyze such TRPL decay in the medium fluence regime, using this model without fitting, which is pretty neat. So if we look at the evolution of the different carriers in the medium fluence regime, so both our electron and hole concentration are going to start at 1 and not, right? Here we've got our trapped electron concentration, so the trapped state, sorry, not trapped electron concentration, the trapped state concentration, which is about 0.25 and not, and our trapped electron concentration is starting at 0, since we don't have any trapped electron at the start. Now you can see there is a, not that this is a logarithmic scale for time, right? So this process is extremely fast. You can see that we've got a very fast decay of the TRPL decay. And this is because electrons, so in purple, are going to be very, very quickly trapped in the trap state. So trapping is much, much faster than any other process. And then it's going to slow down considerably because your trap states are going to be saturated. So you can extract your trap state concentration and T by looking at the height intensity difference between your maximum of the TRPL, or the initial value of the TRPL, and when you see a slowdown in the decrease. So you're going to see this sharp decrease and then something much slower. So by doing the difference between initial value of TRPL and where it starts to slow down, multiply that by N0, you get your trap state concentration, which I think is very neat because it's just a very easy way to get your trap state concentration, which is a very important information, without doing any fitting. Right. So contrary to so contrary to the BT model, the BTD model is a bit more versatile, especially in the low fluence regime, because in the low fluence regime, both your trapping and bimolecular recombinations have a monomolecular process behavior, monomolecular behavior, which means that your TRPL intensity is going to be an exponential decay whose rate is going to be KB P0 plus KT and T. Now, usually KB P0 is much, much lower than KT and T because KT is a very high, it's a very fast process, right? So in reality, KB P0 is going to be negligible and your decay is going to be mono-exponential, which depends on KT and T. However, when you're going to fit your data, the model does not know that. It can't tell that KB P0 is going to be negligible. So what's going to happen if we, like for the BT model, did the same thing, simulated TRPL decays over a wide range of excitation fluences, added a bit of noise, and then used the model to fit the data. And you see the values of KB, KT, KD, KM, and T and P0 are a bit all over the place, especially in the low fluence regime. But if we calculate KM, which is the sum of KB, P0, KT, and T, you can see that it's pretty much 1 all over. And this shows that the model does see that the TRPL is mono-exponential and is going to try any combination of KB, P0, KT, and T, any that satisfies the same value of Km. So that's a bit of a problem because then we can't use the contributions that we previously used to ensure that our fitted values are accurate. So we'll see how we can go past that just after. Now, if we look at the medium fluence regime, there's a very small fluence window where we actually retrieve accurately all of our parameters. Awesome. But you have to find this window, which is very narrow and yeah, it's pretty hard to find. And then if you go in the high fluence regime, you can see that all of your parameters goes badly in terms of accuracy, and except for the bimolecular rate constant, which makes sense because you only have bimolecular recombinations. Right, so how can we ensure that the values we retrieved are correct? Well, so far, I think the only solution is brute force, which is not the best. So yeah, by molecular recombinations. So brute force, what I mean is that you're going to create a grid of gas parameters for your fitting optimization, right? So here we've got A1, A2 gas parameters, and we're going to create this grid of white dots. And then we're going to run the optimization, and we're going to see where each optimization is going to converge towards. So here we've got two solutions of the fit. So that's basically what I did using this model, except that instead of 2 parameters, I've got 1, 2, 3, 4, 5. So I looked at a low fluence TRPL decay, a medium fluence TRPL decay, and a high fluence TRPL decay, and I tried many gas parameters. So you can see in the low, for the low one, we get a lot of different values for KB, KT. I can't see my screen, but yeah, we get a lot of different values. But you can see that we only get one value for Km, which makes sense because Km is the rate of our mono-exponential decay. So all of these values of KB, KB, P naught, KT, and T are going to lead to the same value of Km. Now, in the medium fluence regime, we get 2 solutions for the fit. Which is good, but still not great because we don't really know which one is correct. Obviously, here we know that the one correct is the one on this line, on the 1 line. But a way to determine which solution would be the correct one would be to determine, for example, P naught through a different method. So, for example, Hall effect or something like that. And then in the high fluence regime, you can see that we're obtaining a lot of solutions for all these parameters, but one solution for KB because we only have bimolecular recombinations, right? All right, I hope I'm not too long. But if I run over time, please let me know and I will accelerate. Now I'm going to talk about carrier accumulation, which is a bit tricky to deal with. So TRPL usually measured using a time-correlated single photon counting. And with this instrument, you are going to excite repeatedly your sample. And after each excitation pulse, you're going to measure 0 or 1 photon. So that means that to get TRPL decay, you probably need millions to billions excitation pulse. Now, that means that instead of having our initial condition to be n carrier concentration at time 0 is equal to n naught, we need to consider that we also have some carriers present from the previous excitation pulse. So at excitation pulse P, we'll have so n naught carriers excited from your excitation pulse, and this amount of carriers from the previous pulse. And for the BTD model, it's going to be the same thing. So the electron and hole concentration are going to be increased by n naught plus the carriers present before, and the trapped electron concentration is going to be at time 0 is going to be equal to the trapped electron concentration present in the previous pulse. So let's see how that affects our model. So BT model to start with. You can see that if we use a 25 nanosecond repetition period, here our electron concentration is going to decrease down to 0.4 of the initial value n naught just before the second excitation pulse. Then the initial carrier concentration of the second excitation pulse is going to be 1.4 n naught, and so on and so on. So this is what I call carrier accumulation. And you can see that if we look at the TRPL decay simulated after many excitation pulses with this repetition rate of 25 nanoseconds, it's going to look different from the one calculated after a single pulse, because we are accumulating carriers which are going to affect recombination in the sample. Now, if we were to use a 200 nanosecond repetition period, we would recombine most of our carriers before the second excitation pulse, which means that the initial condition for our second excitation pulse would be exactly the same as the one for first excitation pulse, which means that the TRPL decay after many consecutive excitation pulses for 200 nanosecond repetition period would be almost identical to the one calculated after a single pulse. So what's the takeaway? Well, it's extremely important to avoid carrier accumulation in order to fit experimental decays by simulating a single excitation pulse. You really don't want to solve your differential equation a billion times for multiple reasons, which I will invite you to read my paper at the end for more reasons. But the main reason is it would take way too much time and you don't want to spend that much time. With a BT model, it's extremely easy to avoid carrier accumulation, thankfully. You just need to let the TRPL intensity to reach 0. A good rule of thumb is to let the TRPL intensity to reach 10 to the power of -4 of the initial intensity. Because as you remember, your TRPL intensity is proportional to n squared. So 10 to the power of -4 means that you have about 1% carriers left in the bands between excitation pulses, which is pretty low and enough to avoid carrier accumulation. Now, carrier accumulation in the BTD model is a bit more tricky. And this is because your TRPL intensity can reach 0, but you can still have trapped electrons and holes in the band and in the trapped state. So let's say we use a 15 microsecond repetition period. You can see that we are recombining all of our free electrons, which means that our TRPL intensity is going to reach 0 since it's the product of the electron and hole concentration. But we still have many trapped electrons and holes waiting to recombine because detrapping is an extremely slow process. Now that means that on the second excitation pulse, although we'll have the same initial carrier concentration for electrons, we'll have a different initial concentration for trapped electrons as well as holes. And therefore, the TRPL decay simulated after many excitation pulses is going to look very different from the one after a single pulse. Now, if we were to increase our excitation pulse, that's what I said. If we were to increase our, not excitation pulse, if we were to increase our repetition period at 20 microseconds, you can see that the TRPL decay is going to start converging toward the single excitation pulse decay. And when we are recombining most of our carriers, you can see that the multiple pulse TRPL decay looks like a lot or single pulse TRPL decay. So a good way with this model to ensure that you are recombining all of your carriers and not have any carrier accumulation is first you need to be in the medium fluence regime, which you can easily tell with the sharp decay I talked about earlier, followed by something much slower. So ensure that you are in the medium fluence regime, and then you want to increase your excitation repetition period. Now, if you're not seeing any difference between two excitation repetition periods, then it's fine. You are probably recombining most of your electrons, trapped electrons and holes, so you're good. So what about lifetime-based analysis? It's a very, very common analysis used in paper because it's extremely easy to apply. Unfortunately, the results of this technique, of this model, is not great. So to compare lifetime-based analysis to our BT and BT model, I simulated some TRPL decays with the BT model, and I changed the value of KT. So you can see that as I increased KT, the recombination got faster. And then what I did, so what I did is that I used a bi-exponential model to fit these TRPL decays, which worked perfectly fine. And what usually people do when they look at the bi-exponential model is that they associate the faster component, so 1 here, so amplitude A1 and lifetime tau1, and the longer component, sorry, the faster component is associated with trapping, and the longer component is associated with biomolecular recombinations. However, here you can see that so A1, the amplitude of trapping according to the bi-exponential model, is decreasing as we increase the trapping rate, which does not make sense, as we literally we are increasing our trapping contribution. We are having more trapping, and as well we are seeing, according to the bi-exponential model, we should have more biomolecular recombinations, which is not happening at all. So you can see that the bi-exponential model or mono-exponential model can lead very easily to misinterpretation of TRPL decays. So it is to avoid, it really needs to be avoided. Right, quick words on experimental measurement of TRPL. This is our setup at Swansea University. It's a Life Spec 2, which allows to measure decays between nanosecond and 50 microseconds. It's coupled to a MCP PMT, which can measure up to 850 nanometers, and an NIR PMT up to 1700 nanometer. And then we've got a 405 and 635 nanometers picosecond laser for the excitation source, and then the repetition period can vary between 50 nanosecond and 50 microseconds. And our lasers are powerful enough to drive our sample in the bimolecular regime, which is perfect. And then we can adjust their power to look at all the different regimes using a variable neutral density filter. And I've modified the setup in order to automatically run fluence-dependent measurements as well as repetition period measurements. So it's pretty neat because I can just leave it, do its stuff, and not having to care about it. A problem about measuring TRPL of sample is photobrightening and photodarkening, as Rodrigo talked about. So this is a TRPL decay of MAPI thin film over time. And you can see that not only its absolute intensity is increasing over time, but also its shape, probably due to photobrightening or photodarkening. So this is quite a problem, because when you want to measure TRPL, you don't want your TRPL to change over time, especially that you want to measure it at different excitation frequencies in order to fit them later on. And you can see here, I did two measurement run at 3 different excitation frequencies. And you can see that my second run in dotted line is completely different from the first run, which is driving me insane. But with a bit of perseverance, you can see that it's possible to manage to measure reproducibly the TRPL decay. And then just a note on how to use fitting. I think it was interesting because I spent a bit of time during my PhD trying to find out how to fit multiple decays, because what you want to do here is global fitting. Instead of fitting each decay individually, you want to apply the same model to all of them and just change the initial carrier concentration in the model. So to use global fitting, it's basically the same thing as the least square optimization, where you calculate the square difference between your data point and your model, then sum everything in the curve, and then you sum everything with all the curves. So pretty easy. And then you can estimate the quality of your fit using the R-square value. But if you don't want to do that, which is understandable, considering that you need to write down the code for the bloody models and then write down the code for the optimization, I invite you to use the tool I developed. I will show you quickly how you can use it. If I can see my screen. Right. So the address is here. So it's a very simple tool, which I need to update. It's a bit out of date, but with this tool, you can very easily fit your TRPL-decays using the aforementioned BTD and BT models. So for example, if you, actually I'm going to use this one. So you take your data, download your data, and then, sorry, not download your data. This is example data. So upload your data on the web app. And then the only thing you need to give as information is the initial character concentration. So I'm just going to use this example data, paste it, and then the app will allow you to choose between the bimolecular trapping and the bimolecular trapping detrapping model, and you will be able to change different parameters and get values. And then you can just press run and let it do its thing. There we go. And the software does everything. So it does the fitting, and then it will show you the evolution of the character concentration at the different initial fluences that you used. And it will give you obviously all of the parameters retrieved from the fit. So yeah, it's a pretty nice tool. I had a lot of fun writing it, and I invite you to use it if you ever do TRPL measurements. And I invite you to let me know if you liked it or if you have any recommendation on any improvement I could do. Anyway, going back to my presentation. Right, now I'm going to finish this talk about oh, sorry, I didn't realize you couldn't see the program. You did, sorry, I'm just going to go through it very quickly. Yeah, I guess I'm only sharing my my presentation. Sorry about that. Okay, I'm going to restart my screen sharing. There you go. So yes, this is the, I call that pairs, very original. So you can find it at this address. The website is a bit slow for some reason, I don't know why. Anyway, going through it very quickly. So you can download test data on the web app, or you can use raw data, obviously. So just load the data here. Then you just need to input your initial character concentration, and then you can choose your model. You can set the guess parameters of your different parameters, or you can actually fix the value. I'm actually going to set a guess value for it, and then just press run and let the magic happen. And ta-da! So you can see the fit. Actually, the fit is here. It's so good you can't actually see the dotted line, but this is because this is related data, so it's a bit cheating. And then, as I was saying, it will show you the evolution of the character concentration calculated for each excitation fluence, and obviously all of the parameters from the fit. So yeah, pretty neat. I invite you to use it. And I'm very welcome to any suggestions about it. Right, going back to my presentation and finishing on state photoluminescence. Thankfully, it's a bit easier than time-resolved photoluminescence. So state photoluminescence, you are going to continuously illuminate your sample. So you're going to generate all the time G carriers. And in the steady state, your rate equation is going to be 0. And because bimolecular recombinations are going to be dominant, both BTD and BT model simplifies to this equation, which is the variation of the carrier concentration is equal to how much carriers you are going to generate, G minus the bimolecular recombinations, which is going to be equal to 0 since you are in the steady state. Now you can solve, you can solve this, which give you, oh, I lost my mouse, it's fine. Which will give you this equation for the PL intensity, which is G multiplied by the radiative recombination rate, escape probability divided by the total rate constant. You can also use the PLQI, which will basically allow you to remove the G unknown from your equation, which means that the PLQI is basically the ratio of radiative recombinations, the radiative recombination rate constant to the sum of the radiative and non-radiative recombination rate constants. Now, the problem is if you were to compare two samples with the same value of G, or if you have the PLQI, if you were going to compare two samples, and if you have one sample more emissive than the other, you can't really draw any conclusion from that, unfortunately, because this higher emission from sample A could be explained by a higher KR, for example, or it could be a lower KN, or it could be as well a higher eta escape, or any combination of this. So yeah, it's not great. However, other stuff you could extract from steady state PL. So example of a steady state photoluminescence spectra, I think it's MAPI, maximum intensity at 760 nanometer. So the PL peak usually spreads over a few hundreds of milli-electron volts. And this is due to lattice defects as well as scattering of phonons, and the scattering of ionized impurities. Which means that the peak full width half maximum is a convenient way to qualitatively estimate your trap state concentration. A broader full width half maximum would suggest more trap state in your sample. And the PL peak position is a good indicator also of the sample optical band gap energy. So it's two interesting things you can extract from your steady state peak. So to conclude, so with both of our in both of our models, we are noticing that recombinations in perovskite materials are bimolecular because of the low back exciton binding energy in these materials. And that means that the TRPL intensity and shape is going to depend on the carrier concentration. Then we've got the BT model, which is very easy to apply. It's a very simple rate equation, but it assumes that the trap state concentration is much higher than the photoexcited carriers, which is an assumption which is a bit hard to make like that. I mean, making assumptions is obviously not the best. You want to be a bit more general when using a model. And then we've got the BTD model, which is more complex, but is based on less assumptions. So yeah, it's really when you look at your TRPL decay, choose which model you think is going to fit to match better the TRPL decay. So recommendations when you measure TRPL. You need to, I didn't discuss that, sorry, but your samples need to be thin enough to consider a uniform distribution of the photoexcited carriers. Because if it's too thick, then you would have to consider diffusion of the carriers in the sample. And yeah, it would make things much more complicated, so avoid that. And when I'm saying thin enough, like 200, 300 nanometers, maximum, I would say. Then you need to be aware that recombination processes, because they are dependent upon the excitation fluence, may be negligible depending on the excitation fluence, meaning that information related to these processes, the rate constant, may not be accurately retrieved. So be aware of that. And extremely important as well, you need to avoid carrier accumulation by choosing an appropriate repetition period, which will allow all of your carriers to recombine before the next excitation pulse. And here's some literature to complete your knowledge on that. I think the first paper is my paper. Yeah, it's mine. And then there's a paper by, I think 2 papers by Sam Strengths. That's it. Thank you.
Thank you very much, Emmanuel. It's a great talk, great explanation of something that for all of us is always more complicated than we think it is. So are there any questions in the group? Well, I can quickly start with a question. In your recommendation, basically, I guess you're saying that you should do all measurements, or if you study a system, you should do it as function of fluence and as a function of repetition rate, and find the regime where your results are most likely to be reliable, I guess, right? Or
yes, absolutely, yeah. Yeah, that's basically it. If you end up measuring a sample which is not going to show this very fast decrease of the TRPL followed by something slower, so a sample that would more follow the BT model instead of the BT model, in that case, so you don't really need to care too much about the repetition period, because you just need to ensure that your TRPL is going to reach 0. But yes, fluence, looking at different fluence is absolutely essential.
Right. And have you had any problem with of real samples then of stability as a function of fluence, or?
Yes, stability is definitely an issue. One of the solutions would be to use, the best solution would be to use a nitrogen atmosphere, but even so, I think you would see some photobrightening. But using very low repetition period, very high repetition period, very low repetition rate would be preferable. But obviously that means that your sample will take much longer to measure, right?
Right. Yeah, there's always, so there's still no hands up. So one more question. So you're saying bimolecular recombination dominates in several perovskite systems. I guess it depends maybe on the system as well. There's always this discussion whether recombination is limited by bulk or surface recombination. Now, is that saying the same thing or not? Or could there be bimolecular recombination at the surface as well, at an interface?
I think the difference between bulk and surface is going to be the rate constant. I think the same model can be applied to both surface and bulk, but at the surface, you will probably, the rate constants are probably going to be the same, as a guess. But at the surface, you're going to have much more trap state as expected. So if we take, the BT or BTD model, then I would expect at the surface to have a much wider range of fluences where trapping is going to be dominant, because the trap state concentration and the trapping rate constant are going to be higher compared to the bulk, where the trap state concentration is lower. But in terms of modeling, I think both of the model should be the same between the bulk and surface.
Right. Okay. Excellent. So if there's no more questions, thank you very much. It was a very insightful talk. And then I guess we will continue with Rodrigo for the last module of the course. Thank you.
Thank you, Professor Herco. And now we will wrap everything up. I will try to be brief, but yeah, I'm gonna start sharing my screen now. Please let me know if you can see it, and also let me know if it's pixelated or not. And at the same time, I think, sorry, I'm gonna stop sharing again. I'm gonna share the presentation first, just in case.
It already looked good.
Yes.
Oh, that's good. Good
Yeah.
news.
Yes. Why didn't you show it?
That's great news. But in any case, you have my presentation now, I hope.
Yeah, it arrived.
Okay. Can you see the screen now? Yeah.
We're waiting.
Okay.
There it is. Yes, it's looking great.
Yes. Very good.
Okay.
There you go.
Okay.
Okay. So I'm gonna try to be as brief as I can. At this point in these modules, well, we have discussed several things about perovskite solar cells, and this is just a big summary. In the previous module, or in the second module, I showed you this scheme, and now after talking a little bit about the characterization techniques, particularly photoluminescence, we know that a lot of this internal process can be studied via time resolution photoluminescence and steady state photoluminescence, as well as transient absorption spectroscopy, which we haven't discussed yet. But again, I will talk a little bit about this technique in my presentation. But as you can see, these type of techniques are very versatile, and they can provide you a lot of information about your device. And at the same time, thinking about perovskite films, thinking about perovskite solar cells, we have discussed how can be made solution process. They have very high tolerance to defects. You can pretty much modify the chemical composition for different applications. Very high efficiency, very high versatility. So it sounds all pretty good, but we haven't discussed stability. We haven't discussed yet the problem with lead content and toxicity, the scaling up, and what to do with the perovskites at the end of their life. So we're going to cover that a little bit about those topics in this module, and we're going to start with stability. So one recurrent question and one recurrent problem through these modules has been stability of perovskites. We know that they are very sensitive, particularly to humidity, to oxygen. They are also very sensitive to temperature. They have some intrinsic problems as well. So the idea of this section is to describe the problem of stability of perovskites with that particular topic, and how can we manage to maybe address that problem, or how it has been done. So I'm going to start with moisture. Now, the perovskite crystal is actually very, very sensitive to moisture. It's very sensitive to humidity. As we have discussed before, particularly the organic cations are very hygroscopic. So that makes the crystal, and it's also a ionic crystal, so that makes it very sensitive to water molecules, and it will lead to degradation. So ways to fight, let's say, against moisture is exactly by playing with the chemistry of the perovskite. So for instance, methylammonium lead triiodide, it's very sensitive to moisture, but if you change perhaps the iodide with bromide, which is a smaller ion, it makes the crystalline structure a little bit closer together, and so it can actually withstand a little bit better the humidity. But also by working with all inorganic perovskites, they also well, it has been reported that this type of crystals, this type of chemical engineering can really help to increase moisture stability of perovskites. That's one way to approach this problem. The other logical way to approach this problem is proper encapsulation. So if you're thinking about commercialization, if you're thinking about application, all the commercial silicon solar cells are properly encapsulated, and that is because they need to be protected of the environment, and it wouldn't be an exception for perovskite. So yeah, you can play with the chemistry of the perovskite, and additionally, you can have proper encapsulation to fight against moisture, right? So that's kind of like the way it has been addressed, and I think it's the way moving forward regarding moisture. Now, oxygen. Again, as we have discussed before, oxygen is a problem in presence of free electrons. It can create superoxide that can lead to degradation. So that's something that, of course, we don't really want. And it's actually some ways to address this problem is maybe to have really efficient charge extraction layers that they will extract the excessive charge in the perovskite before it can react with oxygen. So that might be one way to address this problem. Another problem is to just work on a synthesis of our perovskite material with a controlled atmosphere. So for instance, try to reduce the presence of oxygen while we are making the perovskite film, and at the same time try to encapsulate our material. That can be another way to address the problem with stability with oxygen. A couple of problems that are related with each other are they are very sensitive to electric field, and they have some intrinsic problems. Intrinsic problems like ion migration, for instance, which is also very, very related with electric field. So the perovskite is made out of ions, and these ions actually can move around between maybe some vacancies, or maybe can move around through the crystal. And so, for instance, one of these ions that is very mobile is iodide. And iodide likes to react with metals like silver, which sometimes is used as the metallic contact. So that also will decrease the stability of our complete device. So how can we work towards addressing this problem? This is actually quite complicated. But one way to do it, and it has been approved before, is that you can actually, again, control the crystal of the perovskite, maybe try to make a tighter composition, maybe a chemical composition that will reduce ion migration. And then to protect perhaps the metallic contacts, you can use interfaces between, for instance, the perovskite film and the contact. And this has been successfully done. So for instance, in this particular work right here, what they did was they added a layer of graphene between the perovskite and the I think it was the silver contact. And as you can see here, well, this is, for instance, they were following iodide through the layer, and they saw iodide migration towards the metallic contact. But by using an interface, they actually reduced or inhibit the migration of iodide towards silver. So that's one way that you can actually maybe address this problem. Now, another problem is temperature. In this particular paper, they said, okay, temperature, because the different crystalline phases of perovskites might change if you change the temperature. And that's, of course, true. When you work with MAPI, for instance, the phase that we're looking for to work with is the tetragonal phase. But if you go a little bit higher temperatures, you can actually change the tetragonal phase to cubic phase. And that's not good. And that happens around 60 degrees. So yeah, for MAPI, it's true. You have to be aware of the transition of the crystalline structure. But it's also it would also depend on the chemical composition of your perovskite. So for instance, for mamidinium lead triiodide, actually the phase you're looking for is the one that appears around 150, 185 degrees. 5 degrees. And But if you go to room temperature, if this phase, which is the black phase, goes to room temperature, it will degrade to a yellow non-photoactive yellow phase. And for instance, for cesium-lead triiodide, which is a all inorganic perovskite, the phase that you're looking for is the tetragonal, but this one is only stable at certain temperatures. So it's definitely a problem. But the way to deal with that, I think, is to work towards the perovskite composition to modify the crystalline structure. But there's really not a lot that you can do about that besides that. And also for the stability with organic cations. So these organic cations tend to be not very stable if you increase the temperature, so that will lead to degradation. So that's the purpose of all inorganic perovskites, for instance, to increase the stability towards temperature. Now we have discussed, well, I have mentioned some of the stability problems that you might have with perovskites and maybe some ideas on how to address them. But then if you think about it, some of them might be solved, or maybe you can use encapsulant materials to combat some of these stability issues. Now, when you think about encapsulant materials in general for a photovoltaic device, for instance, they have to fulfill several functions, which I haven't listed here. The first one is they need to be they need to have very high transmission. They need to protect you about the weather, the environment. They have to give you a structural support. They have to isolate the material, the physical isolation from the environment, electrical isolation also from the cells during fabrication, handling, storage. They have to also be resistant to hydrolysis, to UV radiation, to thermal degradation. They have to be cost effective. They have to also have a proper expansion coefficient without cracking, because the solar device will be in the roof. So that's also very, very important. And they also must protect your material from oxygen and water. So these are requirements for any photovoltaic device, very nice summarized by Cody and Amhat in this table right here. These are some of the parameters, but this is usually the case for any photovoltaic device. But when you're thinking about perovskites, you need to consider additional things, as you know. For perovskites, we need to make sure that whatever encapsulant material that we use, it doesn't really react with the perovskite layer or with the solar cell. We have to make sure that, for instance, if we're using a resin, the curing temperature will not degrade the perovskite layer, or will not produce gases that might react with the perovskite layer. And it also has to be maybe flexible enough if we're looking forward to, if we're trying to deposit the perovskite film on flexible substrates. So we need additional considerations, particularly for stability. So some approaches that have been made towards encapsulations for perovskites. Well, the first starting point was to use the ethylene vinyl acetate, or EVA, which is the encapsulant material they will use for commercial silicon devices, because it's cost effective. It has very high transmittance. It has worked very well for silicon. It's the most used material for silicon devices. And as you can see here, it has been used in a couple of perovskite configurations. In this case, a tandem device. In this case, just a regular perovskite device. And so I'm going to give you some of the results of these experiments. They use a tandem device right here. And so they actually found out that by encapsulating this material with EVA, they managed to get 1,000 hours of damp heat test. That is 85 degrees, 85% relative humidity for 1,000 hours and the cells were completely stable. However, because EVA has a curing temperature of around 140 degrees, I believe, they need to have an additional buffer layer, tin oxide and zinc tin oxide, to protect the perovskite film. So they needed a perovskite configuration that can withstand high temperatures. So they use a cesium formamidinium lead halide, which is a mixture of iodide and bromide, in order to be able to do that. And then in the second experiment right here, they were able to sustain 90% of the initial efficiency after 200 thermal cycles. I think they went from -20 to 80 degrees or something like that. But again, in this configuration, they also had to use a buffer layer. So it seems to work for perovskite composition that can withstand high temperatures, but it's not, because of the current temperature of 140 degrees, is not very suitable for all the perovskite configurations. So you have to, it's something that you have to be aware of. And it also has been reported that EVA, if it's degrading, it can create acetic acid, and then the acetic acid can react with the perovskite film. So it will eventually lead to degradation. So EVA might work, but then you have to consider the chemical composition of your perovskite, and you might need to use additional buffer layers in order to make it work. Another encapsulant material they have tried to use, it's polyisobutylene, which is this black stuff right here. It's usually used for sealing edges, I think on CIGS technology. And they actually try different configurations, and this is also, that is, I believe, something that is quite important. So for instance, in this configuration right here, which is called the blanket configuration, they just have the complete device and then just put the PIV everywhere. So it's completely covered, so it's completely isolated. The cells work nicely, and actually in the blanket configuration, which is this one right here, they managed to get 200 thermal cycles, 550 hours of damp heat testing, and the device remain efficient, which is really good. So this means that this chemical did not react with the perovskite and was able to protect the perovskite. However, there's another thing that we need to consider when thinking about encapsulant materials, and we will talk about this a little bit later, but it is, what are we going to do when at the end of life of the perovskite, right? If we have something like this, how will you be able to recover the materials inside of your device? So this might protect your perovskite, but then it's probably everything will be lost after that, right? Because you won't be able to recover some of these materials. In contrast, these configurations where you only use perhaps an encapsulant material on the edges might be a smarter design, but the result, although they got like really, really nice stability, it wasn't as good as with the blanket configuration. But it's also important to keep in mind that we have to think about the configuration of our device. We have to think about how to design the encapsulation, thinking about the end of life, and not only about protection. It's something that we have to think about with perovskites. Again, I'm not going to stop a lot right here, but there are some reports for epoxy resins, which it's basically not very good. It releases gases during curing. It degrades the perovskite, but several configurations have been tried, and that's encouraging, of course. And thermoplastic polymers, but as you can imagine, the problem with thermoplastic polymers is that you need temperature to melt the thermoplastic, and that might affect your perovskite. So it's not ideal. Some out of the box kind of encapsulant materials, which I think are very interesting. In this case right here, for instance, they mix an encapsulant material with a fluorescent component. And so in this way, this fluorescent component transforms the UV light into visible light. So it's a way to protect your film from the UV radiation and at the same time create more usable light for your perovskite. So that's something really interesting to have in mind. And in this case right here, they use atomic layer deposition and chemical vapor deposition to deposit a stack of different materials that will make an encapsulant material flexible. So they have alumina and they have a polymer. And so they have different layers, and this will make the encapsulant material flexible, which will be very useful for flexible substrates. So something to keep in mind. Now, as I mentioned before, for perovskites, we do need to consider additional factors for encapsulant materials, but then we need to add another one, which is the design. We have to think about the end of life. It's not only about protection, but it's also about recovering the materials, right? So we have to find a way to encapsulate our perovskites to protect it, but at the same time that at the end of life, it will allow us to maybe recover as much material as possible. So something to keep in mind for encapsulation of perovskites. Now, I'm jumping now towards toxicity of materials and green chemistry. When we think about toxicity of materials, we tend to think about, okay, you have your perovskite crystal, it's all very nice, it works quite well, but you have lead on the crystal. And of course, lead is a toxic component, and we have to think a way of deal with it. And that's on one side. And then on the other side, it's not only lead, but the fabrication of perovskites. We use a different type of solvents. We use different type of materials in the fabrication of the device that might be also hazardous to the environment or health, or maybe we're trying to scale up the technology, we're going to use very large amounts of these solvents, so that can be dangerous. So how can we deal with that? Now I'm going to start with green chemistry. Again, just very slightly, because Professor Matthew Davies is going to talk about this tomorrow. But the idea is to try to look for alternative solvents in the fabrication of the perovskite solar cell that are able to give you as good results as the traditional solvents that we usually use. So in this right part of the presentation, it is a summary of a work of a PhD student, Alex Dulling, which was looking to replace DMF, for instance, in the preparation of perovskite films, and he managed to get some substitution with really nice crystals with different and alternative materials, and efficiency is comparable as with using DMF. So the idea, again, try to use solvents that are greener than some of the nasty things that might be used during perovskites. Again, the invitation towards the presentation of Professor Matthew Davies for tomorrow on this topic. And then talking about lead, the thing about lead is that the perovskite crystal, it's slightly soluble in water. So the worry is that maybe the panel of perovskite solar cells in your roof gets damaged and it starts raining like crazy. And so all this will be leaked, all this lead will be leaked to the ground, right? And that's, of course, a big concern, and that's something to keep in mind. However, well, and that is the reason why there is, well, because of lead concern, there's regulation of lead usage in electronic materials. And yeah, and so for instance, one of these regulations from the European regulation of hazardous substances is that you should have less than 0.1% in homogeneous materials of lead. In the perovskite film, lead comprises more than this. So it's something to keep in mind, although this does not apply for photovoltaic panels. This is just a reference to remember that we have to be aware of lead usage, of course. However, for perovskite solar cells, the quantities that we use per square meter are roughly 400 milligrams or so. So it's not really a large amount of lead per square meter. So it's a problem. It's something that we have to consider, but to remember as well that we don't have to use a lot, or there won't be as much lead in the final device as you might think. And there's some reports about this, but one very interesting experiment was made by Heligno, where they imagine a catastrophic scene on a photovoltaic farm. What will happen if all types of rain will completely dissolve the lead iodide to the ground? What will happen? And his results show that it will be undesirable, but a bit far from catastrophic. He predicted 70 parts per million of lead, where you can find 50 to 200 lead already in urban areas. So of course it's a problem. Of course it's undesirable, but we have to also have a little bit of perspective on it and have ways to deal with it, I think. Now, let's say that we don't want LED. So what can we do then to substitute LED? And so some people thought, okay, so instead of LED, let's use different materials. And one of the first or the main substitution has been tin. The problem with tin is that, first of all, it's not very stable. He likes to be in +4 oxidation state. So it's a bit unstable on crystals, as tin too. But also that the efficiency of this substitution is not very high. Also is as toxic as lead. And as Professor Matthew Davies mentioned during his presentation, we probably have to think about not using a lot of tin because there's not, I don't think, a lot of it, particularly if we're planning to use it for FTO. So maybe, yeah, we need to, maybe it's not the way to go, right? But then there are another alternatives like copper, bismuth, germanium, antimonium, and silver. However, none of them has yet arrived to the efficiency and stability of lead perovskites. So if that's the way to substitute lead, we're a bit far away yet to get there. So then how to deal with lead? So if we're going to use lead, how can we deal with lead to avoid any catastrophic, well, any problematic leakage or something like that? And the first of all, it's proper encapsulation. You have to make sure that you have an encapsulated material that can actually protect your device. And yeah, to avoid release to the environment, we need to find a good way to encapsulate our material. And the next one is after the end of life of the device, of the solar cell, we have to find a way of deal with the lead. And one option will be recycling. So there's a lot of effort right now to try to make sure that we can recycle as much or recover as much lead as possible from the device, but also to recover some of the materials like gold or maybe the substrates, the FTO. And here are 3 examples. The first one that I show you, you have a complete device. You remove the metallic contacts with adhesive tape. You dissolve the whole transport material with a solvent, an organic solvent probably. And then the perovskite layer, you dissolve the methyl ammonium iodide, or maybe you burn it. And then you have a lead iodide film that you can recover. And then you can use in a solution, and then you can use this solution to make a new film. And so this way you reduce any release of lead. So this is one approach, usually the most common approach, to recover lead iodide, and then with lead iodide to create more perovskite films. Another very interesting approach is to use regeneration of the perovskite film. So here you use a methyl ammonium gas to improve the crystallinity. And then let's say that you have a device that has been degraded a little bit, and then you have like a couple of holes right here. So what you do is you just pump a little bit of methyl ammonium gas to regenerate probably the methyl ammonium that you have lost in your perovskite film. And so this way you don't really have to disassemble the perovskite cell. You can just regenerate it through the flow of methyl ammonium gas. So that's a very interesting approach. And they found out that yeah, the efficiency of these samples, well, might drop a little bit, but still works quite well. And then for different configurations, it's the same thing. It's try to recover as much as possible. In this sample right here, they have a carbon electrode. And so what they did was to dissolve the perovskite, remove the carbon electrode, and then the perovskite solution. What they eventually did was to precipitate and to obtain lead iodide, and again recover lead iodide to make a new film. So these are some examples of recycling of perovskites, mainly focusing on recovering materials and recovering lead. Now about scaling up the technology. In the ideal scenario, you will have everything solution process that looks something like this, where you can deposit the perovskite film through a solution process, but not only the perovskite film, but all the different layers in a roll-to-roll system. That will be ideal. But some things that you have to consider when looking to scale up the technology is that whatever works in a small scale does not necessarily mean it will work on a large scale. you have to find, again, the proper conditions for deposition. You have to find, you have to think about all the logistic problems, all the problems that will rise up naturally by scaling up the technology, because it's not only for perovskites, but also for the additional layers. You might have new stability problems. You might have to think about different or alternative designs. And you also have to be aware of the environmental impact of scaling up this technology. So you have to think about using proper solvents to do it. Now, I'm going to focus a little bit on the deposition techniques. As I mentioned before, usually in a very small scale, you will use a spin coating. However, this technique is very wasteful and is not very useful for large scale if you want to make modules or something like that. You need to find a way to have perovskite films with good properties as you get in a small scale, but with different type of deposition techniques. And I'm gonna talk a little bit about this. So for instance, one technique is vapor deposition. You can get very, very homogeneous films with this type of technique. You basically evaporate the material on your substrate. I think this technique is also used for thin film solar cells. It's very reproducible, but it does require specialized equipment and specialized conditions, so it's a bit tricky. Another technique is blade coating. In this technique, you have your precursor solution, and then you use a blade to spread it through the substrate. Now the substrate can be heated up, and then you will start to have a crystallization of your perovskite film. This can also be used for flexible substrate, as they have demonstrated in this work right here. And with this type of technique, I have found deposition rates of 180 meters per hour, and efficiencies as high as 15.3% in large areas, like 33 centimeters squared. So blade coating, definitely an interesting option. The next step after blade coating will be slot die coating. So in this technique, you have your perovskite precursor solution, and then you inject this solution into a nozzle that looks something like this. And so the nozzle will deposit the precursor solution into your substrate. Of course, there are several parameters that you have to think about, like the separation, maybe the viscosity of your solution. But with this technique, again, you can deposit on large scale areas, and this will be the technique, for instance, to use in a roll-to-roll deposition, where you can actually move the substrate, or maybe you can move the nozzle. Traditionally, you will move the substrate at different speeds, and then you can make a deposition of a very homogeneous film. And again, this has been done for perovskites as well. It's probably the most promising scaling up technique for perovskite films, particularly for flexible substrates. And another very interesting technique is the screen printing, because with this technique, you can actually print either a lot of small devices or very large area devices. This is useful for carbon devices, where you can deposit each mesoporous layer via screen printing, and then just infiltrate the perovskite solution, and then anneal your samples. And with this type of deposition here at specific, just by reducing by increasing the active area of the material, 100 square centimeters, 10.5% efficiency has been achieved, which is also very, very promising. And now, just to wrap everything up, talk a bit about the end of life of perovskites. So it's more about thinking about the weight of recycling, or what to do at the end of life of the perovskites. So in order to do that, we need to take a look of what it already exists, like a silicon solar cell or thin film solar cells. Now, this very beautiful diagram, you can find it in GridMatch. I think it's very, very nice. But these are just the recycling process for both of these technologies. So silicon is here on the left, and thin film technologies is here on the right. So for instance, for silicon, cells, you will take your silicon solar cell, you will disassemble to remove the aluminum frame. You will burn the solar cells to remove the encapsulant material. And then you will try to recover as many wafers as possible and then reuse them. And the ones that you cannot really recover them, you will melt them and use the silicon there. In this way, you can use 95% of the glass. You can recover most of the well, it says here 100% of the metal that you have on your frames. And yeah, so it works really well for silicon solar cells. For thin film devices, however, what they do is they take the module, they shred everything into pieces, and then they dissolve the components with strong acids and perovskites. Peroxides, and so they dissolve all these very valuable metals, and they will try to recover all of these components as well. So they precipitate and then separate the different metals, and they can recover the semiconductor materials. And yeah, they remove the encapsulant, and they, of course, you will have pieces of glass, and then you can recover the pieces of glass and recycle it. So these are the two current technologies that exist right now, but then we have to think, okay, what might work for perovskites? If we go back a little bit to the presentation of Professor Matthew Davies, he mentioned that it is predicted that the most expensive or the estimated relative cost of your perovskite field, the most expensive one will be the conductive, transparent conductive oxide, the FTO in this case, right? So if this is the most expensive bit of the perovskite film or the perovskite solar cell, then we probably cannot go and just shred it like in the thin film technologies, right? So probably this route is not useful for perovskites. We need to find a way of recycling where we can recover as much material as possible. So let's go this way. So let's try to disassemble, and then, okay, so in order to recover the FTO, we need to find a way to remove the encapsulant material, because we cannot burn it. If we try to burn it, we will lose the perovskite film, right? So we need to find a way to remove the encapsulant material. And that also leads to design. How can we design the solar cell in a way that we can actually remove the encapsulant material without damaging anything inside of the solar cell? So alternative configurations or alternative designs are required in this way, and maybe not burning the encapsulant material, but find a way to dissolve it so we can remove the glass maybe, and then sequentially separate perhaps the metallic contact, and then the whole transfer material, we can dissolve it, then we can dissolve the perovskite and all the different components. This way we can actually recover the FTO. This way we can actually recover some of the materials. We will avoid lead leakage and yeah, try to reduce waste as much as possible. But as you can see here, it implies not only a way to do it, but a way to think it, a way to design. We have to consider a little bit more things when working with perovskites in comparison with silicon or thin film devices. That will be it. Just some final thoughts. We really hope that after this tutorial, you have learned about circular economy and how it is important to adapt that type of mentality, maybe reusing stuff. Also, I hope a little bit about of the generalities of the general knowledge that there is about perovskites, the challenges there are, and the opportunities that there are right there. And also, we are a photochemistry group, so I also hope, or we also hope, that you have that you can take away a little bit about photoluminescence characterization. Again, an invitation for the presentations tomorrow for Professor Matthew Davies and mine, if you wish. Here are the presentations and the time scale. Again, we are Applied Photochemistry Group. If you're interested, you can always contact us. And thank you again for your time. Thank you again for your patience, and to the organizing committee for the invitation. Thank you very much. I don't know if you have any questions.
Thank you very much, Rodrigo. That was a very nice presentation. Are there any questions from the participants? Any hands? I guess people are getting hungry.
Yeah, that's it's understandable.
Dana,
Yeah,
go ahead.
okay, yeah, maybe I can go. Rodrigo, as your last slide, you were mentioning that for the thin film technology, the recycling process that they shredding everything, right? I don't know, because I remember that many of those, let's say, second generation photovoltaics, usually to calculate the levelized cost of energy and those things, usually they imagine a production line with the deposition of ITO by sputtering on the glass. So I'm not sure. I mean, you said because that maybe is not an option for perovskite because of FTO, and you don't want to shred everything together, right? But I think for second generation PV also you have that valuable substrate that maybe you don't want to shred everything together. I'm not sure.
Yeah,
data on that.
Yeah, I agree completely with you. I know for sure that maybe there are some companies over there that will recycle the thin film technology in a different way, but from what I could find, you will usually shred everything and then try to recover the metals. So maybe you can recover a little bit of indium if you dissolve it properly at the end. But yeah, I don't think that will be an option for perovskites anyway, because of all the additional problems, of course. And again, maybe silicon solar cells and maybe thin film technology was developed some time ago, but now I think the challenge is to design the next generation with this in mind. Not only that it works, not only that it's efficient and cost effective, but also thinking about what to do at the end of life. And so maybe that was a problem before, but I don't think we have that option for perovskites.
Okay, right. Thank you very much.
Yeah, I just also add that with what tends to happen is that it's a positive and a negative. We end up using such small quantities that sometimes you need so much material to recover enough ITO or not enough indium to make it worthwhile, that's simply not there, if that makes sense. So unless we design things a little bit better that are easier to extract these materials in very small quantities, often it's not worth it. I mean, it depends, it's not worth it economically for people unless they stockpile and have very efficient processes. So that's one of the challenges as well going forward.
Right, thank you.
Very good. Any other questions from anybody? If not, I had a quick question on the lead, which is always the Mahmoud. I'll continue after Mahmoud. Mahmoud, do you want to ask a question?
Sure. Thank you, Doctor. Just a small question about the recycling process of the silicon-based solar cells. As what I know, that silicon-based solar panels also use lead tin solder in the panel. So I was just wondering if there are established procedures or protocols to deal with the lead, whether recycling the lead or a safe disposal for that lead.
Yeah, that's true. When you think about the lead problem with perovskites, a lot of people brought that up, right? So you have lead on some of these solders. I'm not really sure what they do with the soldering wires. I don't know if you might know something, Matt.
So certainly they have to ensure safe disposal. I can't say much more other than I know the silicon community are working very hard to develop lead-free solders also, and I think there's significant developments there. They've cut down the amount of lead they use in solder quite a lot, but still they do tend to use lead-based solders, but I think they're trying to eradicate that completely, so that would be the best step. What I would say is, what I know of silicon recycling is it's currently quite wasteful, so I would imagine that they just ensure safe disposal, but I may be incorrect there.
Oh, okay, thank you very much. I was just wondering that because if they already have like just protocols to recycling protocols, so the perovskite community would build up on that, but if they don't have it, it's like
yeah. I guess the difference, because often people in the perovskite community will say, well, actually they use more lead in silicon than they do in perovskites, and that is true in the solder. But the big difference between the two systems, of course, is that the lead that we use in perovskite is water soluble, so that's straight away problematic in terms of a potential route to leach to the environment significantly if we don't manage it.
Okay, I see. Yeah, thank you, Doctor.
Okay.
Thank you. That was exactly also my question. So if there's nobody else, then I would like to thank everybody for their participation in the course, especially, of course, the professors that took their Sundays to teach us about their passion for photovoltaics, perovskites, and everything that goes with it. So thank you all very much, and we'll close the course. I think there will be, okay, so Mariana is gonna give some more details on other aspects of the course, but I say bye and see you hopefully all tomorrow in the symposium C7.
Thank you
That's
so
great.
much,
Thank you.
everybody, for the time and for attending this course. Thank you. It's time to end this meeting. And then we thank you all for your participation. It is an honor to have you participating in each year, and we hope to see you soon. We know that this time is difficult for all of us because of pandemic, but nothing is impossible. You know that of us, like human, we commit some mistakes, but here we are. And then we have here a diploma, some diplomas. Let me try to share my screen first. Just let me know if you could see it. Can you now see it?
It's just loading. Yeah, there you go.
Okay, got it. Just right. Okay, here we have like the diploma from Rodrigo García Rodríguez. It was an honor to successfully completing this module. Thank you so much. We have other one here from Matthew Lloyd Davies, if it's pronounced in a correct way. Sorry if your full name is not pronouncing that.
No, that's correct. That's correct.
Got it. Thank you so much. And then for the last one, we know that we had in last moment another participant who is Emmanuel Pin. Emmanuel, you are not in the role. So if you want your diploma, it will be great if you send a Gmail to the organizing for the Congress. So then that will be all. Thank you so much again. And just to give you a reminder, this diploma, it's going to send you via Gmail. You write your email at the page from the Congress. So that will be all. So you have a question, or does anybody have other question or thoughts? We're here, but I suppose is everything okay, right?
Yeah, that's great. Just thank you very much from us. It's been a pleasure. I hope everyone's enjoyed.
Thank you all of you. Have a good grade. We hope you are safe and healthy at your home, and we hope to see you soon. Thank you, everybody.
Thank you.
Thank you.
Thank you.
Great,
See
thank
you
you all.
tomorrow.
Bye, see ya.
Bye bye.